Langchain Voyage AI Embeddings Voyage AI Embeddings. A comprehensive breakdown of its functionality and significance. Voyage AI Embeddings is a langchain embedding class that leverages the Voyage AI embedding model for efficient text representation and retrieval. Voyage AI Embeddings provides a streamlined approach to embedding text within langchain, facilitating powerful semantic search and retrieval capabilities. This class encapsulates the complex process of embedding, enabling seamless integration into langchain applications. Component 1. Langchain is a powerful and flexible framework that provides a wide range of tools for building and deploying language models. It offers a modular architecture, allowing users to easily combine different components, such as embeddings, prompts, and chains, to create customized language-based applications. Langchain simplifies the process of working with large language models (LLMs) by providing a structured way to interact with them and utilize their capabilities. For example, langchain can be used to build chatbots, document question answering systems, and summarization tools. Component 2. Voyage AI Embedding Model is a transformer-based model specifically designed for text embedding. It utilizes advanced deep learning techniques to generate high-quality vector representations of text, capturing nuanced semantic relationships between words and phrases. These embeddings are crucial for a wide range of natural language processing (NLP) tasks, such as semantic search, document clustering, and recommendation systems. Voyage AI Embedding Model excels at capturing complex semantic relationships within text, enabling more accurate and relevant search results. Voyage AI Embedding seamlessly integrates with the Voyage AI Embedding Model, a sophisticated transformer-based architecture tailored for text embedding. This model leverages deep learning techniques to generate concise numerical representations of text, capturing its inherent semantic meaning. This approach enables efficient similarity search and retrieval by effectively representing text as numerical vectors, allowing for comparisons based on semantic similarity. Voyage AI Embeddings plays a pivotal role in langchain by facilitating the conversion of text into numerical representations, known as embeddings. These embeddings empower langchain to perform efficient similarity search and retrieval. This functionality enables langchain to effectively find relevant information within large datasets by comparing the semantic similarity of textual data. Embeddings allow langchain to go beyond literal keyword matching, understanding the underlying meaning and context of the text, thus providing more relevant and insightful results. High-quality embeddings generated by the Voyage AI embedding model enable more accurate and meaningful comparisons between text fragments. These embeddings capture the nuances of language, leading to more relevant results in tasks such as semantic search and text retrieval. High-quality embeddings are particularly crucial for applications requiring nuanced semantic understanding, such as information retrieval systems, chatbots that engage in natural conversation, and document summarization tools that accurately capture the essence of the original content. Enhanced search accuracy is a direct result of the high-quality embeddings generated by Voyage AI embedding model. By leveraging these embeddings, langchain can perform semantic searches, going beyond simple keyword matching to understand the underlying meaning of text. This leads to more accurate results, especially when dealing with ambiguous queries or complex search criteria. Enhanced search accuracy is particularly beneficial for applications where precision is paramount, such as legal research, scientific literature analysis, and medical diagnosis. Scalability for large datasets is essential for handling the ever-increasing volumes of text data. Available today. Voyage AI embeddings. Powered by the Voyage AI embedding model, is designed to handle large datasets efficiently, generating embeddings for vast amounts of text without compromising performance. Scalability allows langchain to effectively process and analyze massive amounts of data, making it ideal for applications such as search engines, knowledge bases, and social media analysis. Potential latency issues may arise due to external application programming interface API calls required to generate embeddings using the Voyage AI embedding model. This latency can be particularly noticeable when dealing with real-time applications, where rapid response times are crucial. To mitigate this challenge, consider optimizing API calls, caching results, or exploring alternative embedding models with lower latency. Dependence on Voyage AI application programming interface API for embedding generation introduces an external dependency. While Voyage AI provides a robust and reliable service, it's important to be aware of potential disruptions or changes in the API that could affect the functionality of Voyage AI embeddings. To mitigate this dependency, consider exploring alternative embedding models or investigating ways to integrate with other embedding providers to diversify your embedding generation strategies. Voyage AI Rank. A description of the Voyage AI Rank system, which utilizes langchain to integrate with the Voyage AI application programming interface for re-ranking large language model results. Re-ranking results returned by a large language model using Voyage AI's ranking application programming interface. Component 1. LangChain is a framework that enables the creation of powerful language model applications by providing a unified interface for accessing and combining various language model tools and resources. Component 2. Voyage AI's ranking application programming interface is a service provided by Voyage AI, allowing developers to submit a list of items and receive back a ranked list based on a set of criteria. This interface allows for the prioritization of results, helping users find the most relevant information quickly. Utilizes langchain to integrate with Voyage AI ranking application programming interface. Enhancing large language model results by re-ranking using Voyage AI's application programming interface. Improved results quality. By leveraging the Voyage AI's ranking application programming interface, the system can reorder the results returned by the large language model, putting the most relevant information at the top. This can significantly improve the user experience, as they are more likely to find the information they are looking for quickly. Enhanced relevance. The system can ensure that the results presented to the user are highly relevant to their query. The Voyage AI application programming interface provides a mechanism to tailor the ranking criteria to the specific needs of the application, allowing for a more personalized and relevant experience. API key management refers to the processes and procedures involved in securely storing, accessing, and rotating application programming interface keys. In the context of Voyage AI Rank, ensuring that the API keys used to communicate with the Voyage AI application programming interface are properly managed is crucial for maintaining security and preventing unauthorized access. API request handling involves the procedures for sending requests to the Voyage AI application programming interface, receiving responses, and handling any errors or exceptions that may occur. This includes tasks such as formatting requests, handling rate limits, and processing responses effectively. LangChain upstage layout analysis parsers validate API key definition. Detailed definition of the variable goes here. Components. Component 1. The validate API key function within the langchain upstage library is responsible for ensuring the validity of application programming interface keys used for accessing external services. Component 2. It acts as a gatekeeper, verifying the application programming interface keys format, structure, and potential validity against the service's requirements. For example, it might check for specific patterns in the key, its length, and potentially even compare it against a list of known valid keys. Architecture. Description of the architecture supporting the variable. The validate API key function is often integrated within the layout analysis parsers component, ensuring that any external application programming interface calls made for data processing and analysis are properly authorized. This means that before any data is sent to or retrieved from an external service, the validate API key function checks the application programming interface key provided to ensure the request originates from a legitimate source. Role. Explanation of the variable's role in the system. This function plays a crucial role in maintaining security and proper access control for external services integrated with the langchain framework. By verifying the application programming interface key, it prevents unauthorized access to sensitive data and resources, ensuring that only authenticated users or applications can interact with the external services. Advantages. Ensures the security and integrity of application programming interface calls made to external services. This is essential in preventing unauthorized access to potentially sensitive information, ensuring data integrity, and maintaining trust in the system. Prevents unauthorized access and misuse of sensitive resources. By rigorously validating the application programming interface key, the system can effectively block unauthorized requests, safeguarding confidential data and preventing malicious actors from exploiting vulnerabilities. Challenges. Ensuring compatibility with diverse application programming interface key formats and validation procedures. Different external services might have unique requirements for their application programming interface keys, requiring the validate API key function to be adaptable and support a variety of formats and validation methods. Maintaining efficiency and minimizing latency in application programming interface key validation processes. The application programming interface key validation process needs to be fast and efficient to avoid slowing down the overall workflow. Striking a balance between security and performance is crucial in designing this function. The Upstage vector store relies on Upstage Redis as its primary storage mechanism for embedding data. It leverages the key-value storage features of Redis to efficiently store and retrieve embedding vectors. Redis in-memory nature contributes to fast retrieval speeds, while its persistence mechanisms ensure data durability. Role. The Upstage vector store serves as a fundamental component in embedding-based information retrieval systems powered by langchain. It facilitates efficient and scalable storage and retrieval of embeddings, enabling applications like semantic search, question answering, and document summarization. Imagine using this to build a search engine that understands the meaning of your search queries, rather than just matching keywords. Advantages. The scalability of Upstage vector store is a significant advantage. Due to the underlying scalability of Upstage Redis, it can handle substantial amounts of embedding data. This enables efficient management of large datasets, a crucial aspect for many information retrieval tasks. For example, this allows you to build a search engine that can handle a massive amount of data, like all the books ever written. Speed is another key advantage of Upstage vector store. The in-memory nature of upstage Redis ensures swift embedding retrieval. This rapid access to data is essential for applications that require quick responses, such as real-time search or interactive question-answering systems. This can improve the user experience of a search engine by providing faster results. Challenges. A notable challenge with Upstage Vector Store is the cost associated with using Upstage Redis. Being a paid service, the cost can escalate as the volume of stored data grows. It is essential to consider the financial implications when deploying large-scale embedding systems. Another challenge is that Upstage Vector Store might offer a limited set of features compared to other vector stores in the market. This could restrict its capabilities for specific use cases, while it provides the core functionality for embedding storage and retrieval. It may lack advanced features like specific indexing strategies or specialized search algorithms. Voyager AI provides a cloud-based platform and powerful language models, while langchain acts as the glue, connecting them to create a seamless experience for users. Re-ranking is integrated into the search process to enhance the relevance of results. The architecture combines the best of both worlds, leveraging the advanced capabilities of Voyager AI's language models with the flexibility and extensibility of langchain. Role. The combination of langchain, Voyager AI, and re-ranking empowers users to leverage the advanced capabilities of Voyager AI's language models for re-ranking search results and effectively improving the quality of information retrieval. This tool can be used to improve the search experience for users of a variety of applications, including e-commerce websites, search engines, and knowledge bases. Advantages. This tool improves the accuracy and relevance of search results by re-ranking them based on their semantic understanding. For example, if a user searches for best restaurants in New York City, the tool could use semantic understanding to identify restaurants that are highly rated, have positive reviews, and are located in the city center. This would ensure that the user sees the most relevant results at the top of the search results page. This tool enhances the user experience by presenting the most relevant information at the top of the results list. This saves users time and effort by eliminating the need to sift through irrelevant results. For example, if a user is looking for a specific product, the tool could identify the most relevant products based on the user's search query and present them at the top of the results list. This tool can be easily integrated into existing search applications using the langchain framework. Langchain provides a simple and intuitive API for integrating the tool with other applications, making it easy for developers to add re-ranking capabilities to their existing applications. Challenges. This tool requires careful tuning of the re-ranking model to ensure optimal performance. This involves selecting the right model architecture, training data, and hyperparameters. It is important to carefully evaluate the performance of the model and adjust the parameters as needed to ensure that the model is performing as expected. This tool may introduce additional latency to the search process depending on the complexity of a re-ranking model. The model's complexity will affect the time it takes to re-rank the search results. It is important to consider the trade-off between performance and latency when choosing a re-ranking model. This tool may require significant computational resources to train and deploy the re-ranking model. The model's training process can be computationally expensive, especially for large datasets. It is important to have sufficient computing resources available to train and deploy the model effectively. Langchain Community Vector Stores USearch. This is a detailed description of USearch, a powerful vector search engine specifically designed for langchain. encompassing its definition, architecture, advantages, and challenges. A vector search engine specifically designed for langchain. Components. Component 1. USearch provides a specialized vector search engine designed for use within langchain. It leverages FAISS and HNSW algorithms for efficient similarity search on embedded text. FAISS, or Facebook AI Similarity Search, is a library specifically designed for efficient similarity search, enabling rapid retrieval of similar items from large datasets. HNSW, or Hierarchical Navigable Small World Graphs, is another powerful algorithm that facilitates efficient nearest neighbor search, particularly in high-dimensional spaces. These algorithms are crucial for USearch to perform effective similarity search on embedded text within langchain, allowing for the efficient retrieval of relevant information based on semantic similarity. Component 2. USearch facilitates the interaction between langchain and vector databases. Its integration streamlines the process of embedding and searching data within vector databases, enhancing the effectiveness of langchain applications. Vector databases are specialized databases optimized for storing and querying vector data. USearch acts as a bridge between langchain and these databases, facilitating the embedding of text into vector representations and then allowing for efficient search operations within the vector database. This seamless integration simplifies the process of leveraging vector databases within langchain, enabling developers to easily embed and search data for various applications. USearch facilitates efficient interaction between langchain and vector databases by leveraging specialized search algorithms. Role. USearch acts as a bridge between langchain and vector databases, allowing for efficient embedding and searching of textual data. USearch plays a critical role in enabling langchain to interact with vector databases. It provides the necessary tools to convert text into numerical vectors, store these vectors in the database, and perform efficient similarity searches. This process empowers langchain to retrieve relevant information based on semantic similarity, enhancing its capabilities for tasks such as question answering, text summarization, and document retrieval. Advantages. Advantage 1. USearch offers optimized search algorithms for efficient vector similarity search. USearch leverages specialized algorithms like FAISS and HNSW, which are optimized for efficient similarity search in high-dimensional vector spaces. This optimization ensures that USearch can efficiently retrieve relevant information from large datasets of embedded text, making it a valuable tool for applications requiring rapid and accurate similarity search. Advantage 2. Integration with langchain simplifies embedding and searching within vector databases. USearch seamlessly integrates with langchain, simplifying the process of working with vector databases. This integration allows developers to easily embed text into vectors, store them in the database, and perform efficient searches using langchain's familiar interface. The integration streamlines the workflow and reduces the complexity of leveraging vector databases within langchain applications. Challenges. Challenge 1. USearch is still under development, and its features may be limited compared to mature vector search engines. As a relatively new project, USearch is continuously under development, and its feature set may be limited compared to established vector search engines. This means that USearch might not yet offer the same level of functionality or comprehensive support for all use cases. While USearch's developers are working on expanding its capabilities, it is important to acknowledge that its current feature set may be less extensive than those of Mature alternatives. Challenge 2. Search's performance might not be as optimized as other vector search engines for all use cases. Despite its optimization efforts, search's performance might not be as optimized as other vector search engines for all use cases. The performance of a vector search engine is influenced by factors such as the size of the dataset, the dimensionality of the vectors, and the complexity of the search queries. While search strives to deliver efficient performance, it is possible that other vector search engines might be better suited for specific use cases or datasets. Langchain Community Vector Stores Vector MMR Config. Definition. Vector MMR config is a configuration object used for controlling the maximum marginal relevance MMR scoring algorithm employed in Vectera's vector search system. This configuration object dictates how Vectra selects the most relevant and diverse documents from a vector database in response to a given query. Components. Component 1. Similarity threshold controls the minimum similarity score between a candidate document and a query for that document to be considered relevant. For instance, if the similarity threshold is set to 0.7, then only documents with a similarity score of at least 0.7 with the query will be considered relevant. Component 2. Diversity threshold governs the minimum diversity score between a candidate document and already selected documents for that document to be considered diverse. A higher diversity threshold leads to the selection of more diverse documents, while a lower threshold favors documents that are more similar to the previously selected documents. Component 3. Max candidates represents the maximum number of candidate documents to evaluate during a selection process. Setting a higher value for max candidates allows the MMR algorithm to consider a larger pool of potential documents, potentially leading to more accurate and diverse results. However, it may also increase the processing time. Component 4. Max results specifies the maximum number of documents to return as the final result. This parameter directly controls the number of documents displayed to the user after the search is completed. Architecture. Vectera's MMR algorithm operates by iteratively selecting documents based on their relevance to the query and their diversity relative to previously selected documents. Documents that are both highly relevant and diverse are given preference. Role. Vectra MMR config plays a pivotal role in optimizing the search experience by enabling the retrieval of both relevant and diverse documents. This configuration allows users to fine-tune the selection criteria based on their specific search requirements. Advantages. Advantage 1. Enhanced search results by balancing relevance and diversity by considering both relevance and diversity. The MMR algorithm ensures that users receive a balanced set of search results. This means they get the most relevant documents while also being exposed to a variety of perspectives and information. Advantage 2. Tailored search experience through customizable configuration options. The MMR config provides users with the flexibility to adjust the search parameters according to their specific needs. This allows for a more tailored and refined search experience, leading to better satisfaction and relevance. Challenges. Challenge 1. Setting appropriate thresholds for similarity and diversity can be challenging. Determining the optimal thresholds for similarity and diversity requires careful consideration of the specific dataset and search objectives. Adjusting these thresholds can significantly impact the performance of the search system. Challenge 2. Determining the optimal number of candidates and results can be nuanced. The choice of max candidates and max results depends on factors such as the size of the dataset, the expected query volume, and the desired level of detail in the search results. It's important to find a balance between completeness and efficiency. Langchain Community Vector Stores World. A brief summary of Langchain Community Vector Stores World. Detailed definition of the variable goes here. Components. Component 1. A Python library providing a simple interface for storing and retrieving. Embeddings. This component allows developers to interact with the vector database in a user-friendly manner, without needing to dive deep into the low-level details of the underlying database technology. An example of such a component could be a library like FICE or Annoy, which provides efficient indexing and search capabilities for large-scale embedding datasets. Component 2. A cloud-based vector database that provides high-performance, low-latency search and retrieval. This component is responsible for storing and retrieving the embeddings, enabling fast and accurate search results. It acts as the central repository for all the embedding data, allowing applications to access and query the information efficiently. Some popular cloud-based vector databases include Pinecone, VV8, and Milvus, each offering different features and capabilities tailored to specific use cases. Description of the architecture supporting the variable. A system that uses world as a vector database for storing and retrieving embeddings, and langchain as an interface for interacting with the database. This architecture leverages the strengths of both components, utilizing world-efficient storage and retrieval capabilities for embeddings, while relying on langchain's robust framework for building conversational AI applications. For instance, a chatbot powered by this architecture could use langchain to process user input and generate responses, while world would be responsible for finding relevant information from the stored embeddings. Based on semantic similarity, explanation of the variable's role in the system enables efficient and scalable search and retrieval of information based on semantic similarity. This role is crucial in applications where understanding the meaning of text is essential. By representing text as numerical embeddings, world allows for efficient search and retrieval of information based on semantic similarity, rather than just exact keyword matching. This capability is particularly valuable in domains like question answering, document summarization, and recommendation systems.
Provides fast and efficient search and retrieval of embeddings. This advantage is crucial for real-time applications, where users expect fast and accurate responses. By leveraging Valt's high-performance search capabilities, applications can provide a seamless and responsive user experience. 4. Example: a search engine utilizing Valt could return relevant results almost instantly, even when dealing with large volumes of data.
Allows for easy integration with langchain for building conversational AI applications. This advantage streamlines the development process for building conversational AI systems. Langchain's intuitive framework provides a powerful toolset for integrating world into conversational AI applications, simplifying tasks such as retrieving relevant information, generating responses, and managing interactions. For instance, a chatbot could use langchain to process user input, search for relevant information in world embedding database, and generate responses based on the retrieved data. Requires a cloud-based vector database to store and retrieve embeddings, which can be expensive. This challenge arises from the need for dedicated infrastructure to handle the storage and retrieval of large-scale embedding datasets. While cloud-based vector databases provide scalability and performance benefits, they also come with associated costs, which can be prohibitive for certain applications or budget constraints. This cost can be mitigated by exploring various pricing models offered by different cloud providers or by considering alternative approaches for storing and retrieving. Embeddings can be challenging to configure and maintain, especially for users who are not familiar with cloud-based vector databases. This challenge stems from the complexity of managing cloud-based systems, requiring familiarity with specific APIs and configuration settings. For users unfamiliar with these systems, the learning curve can be steep, potentially hindering the implementation and maintenance of the architecture. This can be addressed by leveraging readily available documentation and tutorials, seeking support from community forums, and collaborating with experts in the field. Langchain Community Vector Stores WorldWorld. A comprehensive description of the World Vector Store implementation within the langchain framework. Detailed definition of the variable goes here. Components. Component 1. World is an open source, high-performance vector search engine that utilizes the HNSW hierarchical navigable small world algorithm. It offers swift and efficient search operations for large datasets. This component facilitates the storage and retrieval of vector embeddings, crucial for efficient information retrieval tasks. Component 2. Langchain provides tools for interacting with large language models (LLMs) and building complex applications. It offers various vector stores to store and search embeddings, a core function in retrieval augmented generation RAG applications. This component integrates seamlessly with World, allowing users to leverage its powerful search capabilities. Description of the architecture supporting the variable. World architecture involves constructing an HNSW graph for indexing embeddings. When a query is received, the graph is efficiently traversed to find the nearest neighbors. This efficient search mechanism is central to World performance and is achieved through the HNSW algorithm, which optimizes the search process by creating a hierarchical structure of neighbors. Explanation of the variable's role in the system. This vector store implementation harnesses the capabilities of World to provide fast and efficient vector search within langchain applications. It empowers users to retrieve pertinent documents or data based on user queries. This role is crucial in facilitating information retrieval, as it allows users to search large datasets of embeddings and retrieve relevant information based on user queries. World significantly accelerates search speeds by leveraging the HNSW algorithm. This enables rapid retrieval of relevant information, leading to faster response times in applications. For example, in a customer service chatbot, this enhanced speed allows for quick identification of relevant customer information, improving the overall user experience. World demonstrates improved efficiency in handling large datasets due to its optimized search algorithm and architecture. This scalability is particularly valuable in applications dealing with vast amounts of data, such as e-commerce platforms or knowledge management systems, for instance. In a large e-commerce platform, World's ability to handle massive data volumes ensures fast and accurate search results for product recommendations. The utilization of World introduces dependencies on its libraries and infrastructure. This might require additional setup and configuration efforts compared to other vector store implementations. It's essential to consider the potential overhead associated with setting up and maintaining World for the specific application. Setting up and configuring Vault can involve a higher level of complexity compared to simpler vector store implementations. This complexity might require more technical expertise in understanding of Vault architecture. However, the benefits of using Vault, such as its speed and scalability, can outweigh these challenges for applications requiring high-performance vector search capabilities. LangChain Community Vector Store Watch a detailed look. A detailed description of LangChain Community Vector Store Watch with its components, architecture, role, advantages, and challenges. Verge is a vector search engine. It can be used to find similar documents using text embeddings. LangChain Community Vector Store Verge is an integration of LangChain and Verge. Component 1. LangChain is an open-source framework for building applications powered by language models. It provides a variety of tools and utilities for working with large language models, including vector stores. For instance, it enables developers to easily integrate language models into their applications and perform tasks like text summarization, question answering, and code generation. Component 2. Verge is an open-source vector search engine that provides a powerful and scalable way to perform semantic search. It offers features such as indexing, searching, and retrieval of vector data. Verge can be used to search through large amounts of text data and find documents that are semantically similar to a given query. The architecture involves connecting LangChain to Verge. LangChain is responsible for generating embeddings from text data. The embeddings are then stored in Verge, which enables fast and efficient retrieval of similar documents. For example, when a user searches for a document using LangChain, the text of the query is first converted into an embedding vector by LangChain. This embedding vector is then used to search the Verge database for similar documents. This integration allows users to leverage Verge's capabilities for semantic search within LangChain applications. It provides an effective way to search through large amounts of text data based on meaning and relevance. For example, this integration can be used to build a question answering system that can retrieve relevant documents from a large corpus of text data. Advantage 1. Efficient retrieval of similar documents based on semantic meaning. For example, this integration can be used to find documents that are relevant to a given query even if the query does not contain any of the exact words in the documents. Advantage 2. Scalable vector search engine suitable for large datasets. For example, this integration can be used to search through millions of documents without compromising performance. Challenge 1. Handling large datasets and maintaining performance can be challenging. For example, it can be challenging to efficiently index and search through large amounts of text data. Challenge 2. Fine-tuning the embedding model and search parameters for optimal results. For example, the choice of embedding model and search parameters can have a significant impact on the accuracy and efficiency of the search results. The LangChain Community Vector Store's Vespa Store leverages the Vespa platform as its underlying infrastructure. Vespa's distributed architecture and efficient search capabilities provide a scalable and reliable foundation for the vector store. The architecture consists of a Vespa cluster, which stores and indexes the vectors, and a LangChain integration layer, which provides access to Vespa's functionality from within the LangChain framework. Role. The LangChain Community Vector Store's Vespa Store plays a crucial role in enabling efficient vector retrieval within LangChain applications. It stores the vectors generated by LangChain models and allows users to perform fast and accurate similarity searches on these vectors. This facilitates tasks such as finding relevant documents, identifying similar entities, and building robust recommendation systems. Advantages: high-performance retrieval capabilities. The LangChain Community Vector Store's Vespa Store leverages Vespa's robust search engine capabilities, allowing for extremely fast and efficient retrieval of vectors. This is crucial for applications that require real-time results, such as interactive chatbots or search engines. Scalable and flexible. The LangChain Community Vector Store's Vespa Store is built on the Vespa platform, which is known for its scalability and flexibility. This allows users to easily adapt the vector store to handle growing datasets and increasing search demands. Challenges: high learning curve for Vespa. While Vespa is a powerful platform, it has a relatively steep learning curve, especially for users unfamiliar with search engine concepts. The setup and configuration of Vespa require a certain level of expertise, which can be a barrier for some users. Integration with other LangChain components. Integrating the LangChain Community Vector Store's Vespa Store with other LangChain components can be challenging, especially if there are compatibility issues or limitations in the available tools. It may require some customization or workarounds to ensure seamless integration with different LangChain components. A summary of LangChain Community Vector Store's VikingDB. None. Detailed definition of the variable goes here. Components. Component 1. A vector store that is built on top of the VikingDB database. This component enables the storage and retrieval of vector embeddings within the VikingDB system. Component 2. A module specifically designed to facilitate interaction between LangChain and the VikingDB vector store. It acts as a bridge, allowing LangChain to utilize the functionality of the VikingDB vector store for embedding related tasks. Description of the architecture supporting the variable. The VikingDB vector store relies on the VikingDB database as its underlying foundation. It utilizes VikingDB's capabilities to store both the vector embeddings themselves and the associated metadata, providing a comprehensive storage solution for embeddings. Explanation of the variable's role in the system. The VikingDB vector store empowers LangChain to leverage the capabilities of VikingDB as a vector store. This integration allows LangChain to seamlessly store embeddings within VikingDB and then utilize these stored embeddings for various tasks. These tasks include searching for similar embeddings, retrieving relevant information based on embeddings, and other embedding-driven operations. The VikingDB vector store is designed to handle large volumes of data and embeddings efficiently. It can scale to accommodate growing datasets and demands, ensuring that its performance remains robust even with substantial data increases. The VikingDB vector store is optimized for speed and efficiency. It leverages VikingDB's efficient data storage and retrieval mechanisms to provide quick access to embeddings, enabling rapid search and retrieval operations. The VikingDB vector store is resource efficient, minimizing the computational and storage requirements for managing embeddings. Its optimized design ensures that it operates with minimal overhead, making it an efficient solution for embedding storage and retrieval. The use of the VikingDB vector store necessitates the availability of a VikingDB database. If a VikingDB database is not readily available, the VikingDB vector store cannot be utilized. The VikingDB vector store currently offers a limited set of features compared to other vector stores in the market. It may lack some advanced functionalities or integrations that are present in more mature vector store solutions. This may limit its applicability to certain use cases or workflows that demand a more comprehensive feature set. LangChain Community Vector Stores Vectra. A summary described as a leaf in YAML format. Vectra is a cloud-based vector database that offers a managed service for storing and querying vector embeddings. Components. Component 1. Vectra Vector Database is a cloud-based service that offers a managed platform for storing and retrieving vector embeddings. These embeddings are numerical representations of data, typically used for semantic search and other natural language processing tasks. Vectra simplifies the process of managing and querying vector embeddings, enabling developers to focus on building applications rather than infrastructure. Component 2. LangChain is an open-source Python library that simplifies the process of building applications. Powered by large language models (LLMs), it provides a framework for connecting LLMs with other tools and data sources, allowing developers to create powerful and flexible AI applications. LangChain's modular architecture makes it easy to integrate different components, including vector databases like Vectra. Component 3. Python is a high-level, general-purpose programming language that is widely used in data science, machine learning, and artificial intelligence. LangChain is built on top of Python, providing a convenient and familiar environment for developing and deploying AI applications. The integration of LangChain with Vectra through Python allows developers to seamlessly leverage both technologies within their projects. Vectra provides a REST application programming interface (API) and software development kits (SDKs) for interacting with its vector database. LangChain integrates with Vectra through its Python SDK. This allows users to leverage Vectra's capabilities for embedding storage, retrieval, and search within their LangChain applications. The LangChain Vectra integration enables users to store and retrieve vector embeddings for various natural language processing (NLP) tasks, such as semantic search, question answering, and text summarization. Vectra as a managed service means you don't need to manage the underlying infrastructure. This includes tasks like provisioning servers, installing software, and configuring security settings. Vectra takes care of all of this, allowing you to focus on developing your application. Vectra's scalability allows it to handle large datasets and complex queries efficiently. This is essential for applications that deal with large amounts of data or need to perform complex semantic searches. Efficient query processing with Vectra's high performance allows for fast and accurate retrieval of relevant information from your vector database. This is crucial for providing a smooth user experience and improving the overall efficiency of your application. Vectra is a paid service, which means there are costs associated with using it. However, Vectra offers flexible pricing plans to suit different needs and budgets. Setting up Vectra integration with LangChain involves configuring the Vectra SDK within your LangChain application. This process might require some technical knowledge and understanding of both libraries. Understanding Vectra's application programming interface (API) is necessary to effectively utilize its capabilities. Familiarizing yourself with the API documentation and available resources can help you navigate the different functions and features offered by Vectra. LangChain Community Vector Stores Upstage Vector Store Summary. NaN. A vector store implementation for LangChain. Leveraging Upstage Redis as the backend for storing and retrieving embeddings. LangChain is an open-source framework for building applications powered by large language models. Upstage Redis is a managed Redis service offering high performance, scalability, and reliability. Component 1. Upstage Redis is a managed Redis service offering high performance, scalability, and reliability. It is a fully managed, in-memory data store that provides high throughput and low latency for a variety of use cases, including caching, session management, and real-time data processing. Upstage Redis is a popular choice for developers who need a reliable and scalable data store. Component 2. Langchain is an open-source framework for building applications powered by large language models. Langchain provides a set of tools and libraries for working with large language models, including tools for data retrieval, prompt engineering, and model selection. Langchain is used by developers to build a variety of applications, such as chatbots, question answering systems, and content generation tools. The Upstage Vector Store utilizes Upstage Redis to store embeddings and their associated metadata. Embeddings are numerical representations of text data, which are used by large language models to understand the meaning of text. The Upstage Vector Store uses Upstage Redis to store these embeddings and their associated metadata, enabling efficient semantic search and retrieval. This vector store provides a means for storing and retrieving embeddings, enabling efficient semantic search and retrieval in LangChain applications. By using embeddings and semantic search, LangChain applications can understand the meaning of text and retrieve relevant information from a large dataset of text documents. Upstage Redis scales automatically to accommodate increasing data volumes and traffic. This means that the vector store can handle large amounts of data without requiring manual intervention. For example, a company that is using the vector store to store product descriptions might need to scale a vector store as it adds new products to its catalog. Upstage Redis can automatically scale to accommodate the increased data volume, ensuring that the vector store remains performant. Upstage Redis offers high-speed access to embeddings, enabling fast retrieval and search operations. This is important for applications that require real-time results, such as chatbots and search engines. For example, a chatbot that is using the vector store to retrieve information from a knowledge base needs to be able to retrieve information quickly to provide a smooth user experience. Upstage Redis provides the performance required for real-time applications. Upstage Redis is a paid service, and costs may vary based on usage. For example, a company that is using the vector store to store a large amount of data might incur higher costs than a company that is using the vector store to store a small amount of data. Configuring and managing a vector store requires some technical knowledge. For example, a developer needs to understand how to configure the vector store, how to index data, and how to perform queries. This can be a challenge for developers who are not familiar with vector stores or with Upstage Redis. LangChain Community Vector Stores VikingDB config. Definition: a configuration class used for establishing a connection with the VikingDB database and defining the parameters for interaction with it. This class acts as a bridge between the vector store and VikingDB, enabling efficient storage and retrieval of embeddings and related text data. Components. Component 1. The host address of the VikingDB server. Either a hostname or an Internet Protocol IP address. It specifies the location of the database server where the vector store will connect and store its data. For example, if the VikingDB server is accessible at dbserver.example.com, this would be the value for the host parameter. Component 2. The port number on the VikingDB server where the vector store should establish a connection. This port is dedicated for communication between the vector store and the VikingDB server. For example, If the Viking DB server is listening on port 5432, this would be the value for the port parameter. Component 3. The name of the specific Viking DB database where the vector store will store and retrieve its data. A database is a collection of tables and other objects that hold data related to a particular domain. For instance, if the vector store is used for storing information about articles, the database name might be articles.db. Component 4. The username used to authenticate with the Viking DB server. This username is associated with an account on the server that has specific privileges for accessing the database. It acts as an identifier to verify the identity of the vector store connecting to the server. For example, the username might be admin for a general administrative account or vector store user for a dedicated account for the vector store. Component 5. The password associated with the username used for authentication with the Viking DB server. This password ensures that only authorized users or applications can access the database. It acts as a security measure to protect the data stored in the database from unauthorized access. Passwords should be kept confidential and not shared. Component 6. The name of the table within the Viking DB database where the embeddings will be stored. A table is a structured collection of data organized into rows and columns. This parameter specifies the specific location within the database where the vector store will store its embeddings. For example, the table name might be embeddings or document vectors. Component 7. The name of the column within the table designated to store the embeddings. A column represents a specific characteristic or attribute of the data stored in the table. This parameter specifies the column where the vector representations of the text data will be stored. For example, the column name might be embedding vector or embedding array. Component 8. The name of the column in the table where the original text associated with the embeddings will be stored. This column allows for retrieving the original text corresponding to a given embedding. For example, the column name might be text or document content. Component 9. The name of the column in the table that will store the document IDs. Document IDs are unique identifiers assigned to each document in the collection, enabling the vector store to keep track of individual documents and their associated data. This parameter specifies the column where these IDs will be stored. For example, the column name might be document ID or ID. Component 10. The connection string used to establish a connection with the Viking DB server. This string encapsulates all the necessary connection information, such as host name, port, database name, username, and password. It acts as a single point of reference for defining the connection details. For example, the connection string might look like Postgres Cloud min password db server.example.com 5432 articles db. Component 11. The function responsible for converting text into numerical representations called embeddings. Embedding functions map textual data into vectors of numbers that capture the semantic meaning of the text. These embeddings are then stored in the database and used for similarity searches. For example, a common embedding function might be OpenAI's text embedding ADA 002 or sentence transformers. OLMPNet base 2. Component 12. The number of documents processed in a single batch during operations like inserting or retrieving data. Batching helps optimize performance by processing multiple documents simultaneously instead of individually. For example, a batch size of 100 would mean that 100 documents are processed together at a time. Component 13. The maximum number of times the vector store will retry an operation if it fails. Retries help handle temporary network issues or other transient errors by attempting the operation. Again, a higher value for max retries might increase the resilience of the vector store, but could also lead to longer delays in case of persistent issues. Component 14. The delay, measured in seconds, between retry attempts. This delay provides a pause between retries to avoid overwhelming the system with requests. A longer delay might be appropriate in case of frequent failures to avoid putting excessive strain on the database or network. Architecture. VikingDB is a distributed, scalable database designed to manage and process large amounts of data. Its distributed nature allows data to be partitioned across multiple servers, enabling parallel processing and improved performance. This architecture is well suited for storing embeddings and text data, facilitating efficient retrieval and similarity search operations. Role. The VikingDB config class plays a crucial role in defining the parameters for interaction between the vector store and the VikingDB database. It specifies the connection details, data storage configurations, and other settings required for efficient operation. This class acts as a bridge, ensuring seamless communication and data transfer between the vector store and the database. Advantages. Advantage 1. VikingDB offers high performance and scalability, allowing for efficient storage and processing of large datasets. Its distributed architecture enables parallel processing, significantly reducing query times and improving overall performance. This advantage is particularly important for applications dealing with large amounts of data, such as those involving large language models or knowledge graph construction. Advantage 2. VikingDB is designed to be secure and reliable, ensuring the integrity and confidentiality of the data stored within it. It implements robust security mechanisms to prevent unauthorized access and data breaches. Its reliability is further enhanced by its distributed architecture, where data is replicated across multiple servers, providing redundancy and resilience in case of failures. Challenges. Challenge 1. Accessing VikingDB requires establishing a connection using a connection string, which includes sensitive information such as credentials, username, and password. Proper security measures should be implemented to protect these credentials from unauthorized access, potentially involving encryption or secure storage methods. Challenge 2. Efficient storage of embeddings and text data within VikingDB relies on careful planning and configuration of tables and columns. The chosen data structures and indexing strategies can significantly impact performance and search efficiency. It's crucial to ensure that the table and column configurations align with the specific requirements of the vector store and the nature of the data being stored. For example, using appropriate data types and indexes for the embedding columns can accelerate similarity search operations. Langchain Community Vector Store Vector Summary. Langchain Community Vector Store Vector Summary, a comprehensive overview of Vectera's role in the Langchain ecosystem. It elaborates on Vectera's definition, architecture, role, advantages, and challenges in the context of Langchain. This summary provides valuable insights for developers and users considering Vectra for their Langchain projects. Detailed definition of the variable goes here. Components. Component 1. Vectra is a cloud-based vector database that provides efficient storage and retrieval of vector embeddings. Vectra stores and retrieves high-dimensional vectors, allowing for fast and accurate similarity search. This is particularly useful for tasks like text search, image search, and recommendation systems. Component 2. Langchain provides a library for interacting with vector databases, including Vectra. LangChain simplifies the process of integrating vector databases into applications, offering a consistent interface for various database providers. This enables developers to easily leverage the capabilities of Vectra for semantic search, question answering, and other natural language processing tasks. Description of the architecture supporting the variable. Vectra is built on a distributed architecture that scales horizontally to handle large datasets. Vectra's architecture enables it to handle large volumes of data and perform fast searches by distributing the workload across multiple nodes. This scalability ensures that Vectra can support real-world applications with massive datasets. Explanation of the variable's role in the system. Vectra acts as the vector database for LangChain applications, enabling efficient search and retrieval of relevant information based on semantic similarity. Vectra provides the back-end storage and retrieval mechanism for LangChain applications, allowing them to perform efficient semantic search. By leveraging Vectra's capabilities, LangChain applications can retrieve information based on its meaning rather than just exact keywords. High-performance vector search and retrieval. Vectra leverages optimized algorithms and hardware to provide fast and efficient vector search. This results in quick response times and improved user experience, particularly in applications requiring real-time search. Scalability to handle large datasets. Vectra's distributed architecture allows it to scale horizontally to handle massive datasets. This scalability ensures that Vectra can support applications with growing data volumes without compromising performance. Cloud-based. Simplifying deployment and management. Vectra is a cloud-based service, eliminating the need for infrastructure management. This makes it easier for developers to deploy and manage Vectra, reducing overhead and allowing them to focus on application development. Integration with LangChain. Enabling seamless interaction with vector databases. Vectra offers a dedicated LangChain integration, simplifying the process of connecting Vectra to LangChain applications. This seamless integration allows developers to easily leverage Vectra's capabilities within their LangChain workflows. Vectra is a commercial service, which may incur costs for usage. Vectra's usage may involve subscription fees or pay-per-use pricing. This cost factor needs to be considered when deciding whether Vectra is a suitable choice for a specific project. Integration with other tools and frameworks may require additional effort. Integrating Vectra with tools or frameworks outside the LangChain ecosystem might require additional effort or custom code, depending on the size of the data. Indexing may take time. Indexing large datasets in Vectra can take time, especially for initial indexing. This might impact application availability during initial setup. Managing access control and security for vector databases. Implementing robust access control and security measures is crucial for vector databases like Vectra, especially when handling sensitive data. Ensuring data privacy and compliance regulations. Vector databases must adhere to data privacy regulations like GDPR and CCPA. Ensuring compliance with these regulations requires careful consideration and implementation. Monitoring and optimizing database performance. Monitoring Vectra's performance is essential to ensure optimal performance and identify potential bottlenecks. This involves monitoring metrics like query latency, indexing time, and resource utilization. Integrating with other vector databases and search engines. Integrating Vectra with other vector databases or search engines might require custom code or specific integrations, depending on the compatibility and functionality. LangChain Community Vector Stores Vectra Summary. None. Vectra is a vector database service that allows users to store and query vectors. Vectors are mathematical representations of data, such as text, images, or audio. Vectra provides a way to store these vectors in a database and then query them using similarity search. This allows users to find data that is similar to a given query, even if the query does not match the data exactly. Components. Component 1. LangChain is an open-source framework for building large language model (LLM) applications. LangChain provides a set of tools and libraries that make it easy to integrate LLMs into applications. These tools include a library of connectors for connecting to different LLMs, a library of tools for working with text and data, a library of chain components for building complex LLM applications. Component 2. Vectra is a vector database service that provides a scalable and efficient way to store and query vectors. Vectra uses a distributed architecture to ensure high availability and scalability. It also uses a variety of indexing techniques to optimize query performance. Vectra is particularly useful for applications that require searching through large amounts of data, such as image recognition, text search, and recommendation systems. Vectra uses a distributed architecture to ensure high availability and scalability. This means that the database is spread across multiple servers, so that if one server fails, the others can continue to operate. Vectra also uses a variety of indexing techniques to optimize query performance. These techniques include locality-sensitive hashing (LSH), approximate nearest neighbor and search, vector quantization. These techniques allow Vectra to quickly find the nearest neighbors of a given query vector, even when the database contains millions of vectors. LangChain and Vectra work together to enable LLM applications to perform tasks that require access to large amounts of data. LangChain provides the framework for building these applications, while Vectra provides the vector database for storing and querying data. For example, an LLM application could use LangChain to connect to a Vectra database and then use the database to search for documents that are relevant to a given query. The LLM could then use the retrieved documents to generate a response to the query. Vectra is efficient because it uses a variety of indexing techniques to optimize query performance. These techniques allow Vectra to quickly find the nearest neighbors of a given query vector, even when the database contains millions of vectors. This makes Vectra suitable for applications that require real-time search, such as chatbots and search engines. Vectra is scalable because it uses a distributed architecture. This means that the database can be spread across multiple servers, so that if one server fails, the others can continue to operate. This allows Vectra to handle large volumes of data and users without sacrificing performance. Vectra is a paid service, so there is a cost associated with using it. This cost can vary depending on the amount of data stored and the number of queries performed. However, Vectra offers a free tier for small-scale use. Vectra can be complex to use, especially for beginners. This is because Vectra requires users to understand vector databases, indexing techniques, and application programming interfaces (APIs). However, Vectra provides comprehensive documentation and tutorials to help users get started. Faster data loading and retrieval. VikingDB, owing to its optimized design for handling vector embeddings, significantly speeds up the process of loading and retrieving data. This efficiency is especially beneficial in applications where frequent data access is required, like recommendation systems and search engines. Efficient querying of vector embeddings. VikingDB facilitates efficient querying of vector embeddings. allowing you to find similar embeddings based on their semantic meaning. This is crucial in applications like semantic search, where finding relevant information based on the meaning of the query is essential. Scalable for large datasets. VikingDB is designed to handle large datasets of vector embeddings efficiently. This scalability is important for applications that deal with a vast amount of data, such as recommendation systems or search engines handling millions of user profiles or documents. Limited to embedding-based search. VikingDB is specifically designed for searching based on vector embeddings. This means that it might not be suitable for scenarios that require traditional keyword-based searching or require additional features not directly related to vector embeddings. Requires familiarity with VikingDB. Using VikingDB effectively requires some familiarity with the database and its specific configuration options. This may pose a challenge for developers not familiar with VikingDB, as it necessitates learning its specific features and functionalities. LangChain Community Vector Stores ZEP Collection Config Configuration Options. None. A ZEP collection config object is used to configure a ZEP collection, providing detailed information about the data within the collection. For example, a ZEP collection config object can be used to specify the name of the collection, the type of collection, the embedding function to use for embedding the data, the dimensionality of the embedding vector, and additional metadata about the collection. Component 1. The name of the collection. It is used for identifying the collection among other collections. For example, a collection named Documents may store text documents. Component 2. The type of collection, such as text or embedding. This attribute specifies the kind of data stored in the collection. For example, a collection of type text would store text documents, while a collection of type embedding would store embedding vectors. Component 3. The embedding function to use for embedding the data. Embedding functions transform data, like text documents, into numerical vectors. For example, a text document can be embedded using functions like sentence transformers or OpenAI's embedding API. Component 4. The dimensionality of the embedding vector. The dimensionality of the embedding vector represents the number of dimensions in the vector space that the embedding function uses to represent the data. For example, an embedding vector with a dimension of 768 will have 768 elements in its vector. Component 5. A dictionary containing additional metadata about the collection. This allows users to store additional information about the collection that is not captured in the other attributes. For example, the metadata may include information about the source of the data, the date the data was collected, or the purpose of the collection. ZEP collections are a key component of the ZEP vector database. They provide a structured way to organize and manage embedded data. Collections offer a mechanism to group and organize embedded data, making it easier to manage and retrieve related information. For example, a ZEP collection might be used to store all of the embeddings from a set of text documents, or all of the embeddings from a set of images. The ZEP collection config object defines the structure and characteristics of a ZEP collection. It provides the necessary information about the collection, including the type of data it contains, the embedding function used to represent it, and additional metadata. This enables the ZEP vector database to understand and manage the collection effectively. Advantage 1. Allows for efficient storage and retrieval of embedded data. By utilizing efficient data structures and algorithms, ZEP collections enable fast access and retrieval of embedded data. This is crucial for applications that require quick search and retrieval of information based on its similarity to other data points. Advantage 2. Provides flexibility in configuring collections for different use cases. ZEP collections can be customized to accommodate a wide range of data types, embedding functions, and metadata configurations. This flexibility allows users to create collections tailored to their specific needs and applications. Challenge 1. Choosing an appropriate embedding function can be challenging. Selecting the right embedding function depends on the specific type of data, the desired level of accuracy, and the available computational resources. A thorough understanding of different embedding functions and their strengths and weaknesses is crucial for making an informed decision. Challenge 2. Optimizing the dimensionality of the embedding vector can be complex. The optimal dimensionality of the embedding vector is dependent on the specific data and use case. Finding the right balance between accuracy and computational efficiency can be challenging and often involves experimentation and analysis. Summary of langchain community vector stores. ZEP vector store. Definition. Detailed definition of the variable goes here. Components. Component 1. ZEP vector store is a vector database that is optimized for storing embeddings generated by large language models. Component 2. It provides a fast and efficient method to perform similarity search and retrieval of textual data. For instance, if you have a large corpus of documents and you want to find the documents that are most similar to a given query, you can use ZEP vector store to retrieve the most relevant documents based on their semantic similarity to the query. Description of the architecture supporting the variable. ZEP vector store utilizes a combination of Zeppelin and FICE to achieve fast and scalable embedding, storage and retrieval. Zeppelin is a distributed data processing system that provides a platform for managing and executing data-intensive workloads. FICE, on the other hand, is a library for efficient similarity search and retrieval of vectors. By combining these two technologies, ZEP vector store can effectively handle large volumes of data and perform similarity search queries with high speed and accuracy. Explanation of the variable's role in the system. ZEP vector store plays a crucial role in language models by enabling efficient search and retrieval of relevant information based on semantic similarity. For example, in a chatbot application, ZEP vector store can be used to retrieve relevant responses from a knowledge base based on the user's query. This allows the chatbot to provide more accurate and relevant responses to user queries, improving the overall user experience. ZEP vector store supports batch indexing and retrieval, which enhance performance and scalability. Batch indexing allows for the efficient processing of large datasets, while batch retrieval enables the retrieval of multiple documents in a single request. ZEP vector store is designed to handle large volumes of data effectively, making it suitable for real-world applications. It is capable of efficiently storing and retrieving millions or even billions of embeddings, which is essential for applications that deal with large amounts of text data. ZEP vector store is relatively new and might not have the same level of maturity as other vector databases. As a relatively new technology, ZEP vector store may not have the same level of features, documentation, or community support as more established vector databases. ZEP vector store requires careful optimization to ensure efficient performance, particularly when dealing with large datasets. This involves selecting appropriate parameters, tuning the indexing process, and optimizing the query execution plan to ensure optimal performance. Vespa store challenges. Requires familiarity with Vespa REST application programming interface. Using Vespa store requires Knowledge of the Vespa REST application programming interface, which can be a barrier for developers who are not familiar with Vespa. This may require additional learning and effort to effectively implement and integrate Vespa Store into an application. Can be more complex to set up and manage compared to other vector stores setting up and managing. Vespa Store can be more complex compared to other vector stores. This is because it involves configuring and managing the Vespa search engine, which requires specific technical knowledge. Efficient retrieval of similar items based on their vector representations. Vespa Store excels in retrieving similar items based on their vector representations, ensuring that users can find relevant information based on semantic similarity. This enables users to discover items that are conceptually related, even if they do not share exact keywords. Advantage 2. Scalable and performant search engine. Vespa Store's underlying technology, Vespa, is designed for scalability and performance, allowing it to handle large datasets and respond to queries rapidly. This makes Vespa Store suitable for applications with high data volumes and strict performance requirements. Advantage 3. Flexible and customizable data storage and retrieval. Vespa Store provides flexibility in data storage and retrieval, enabling users to tailor the system to their specific needs. Users can customize the indexing and retrieval process to optimize for specific use cases, enhancing the efficiency and effectiveness of the vector store. Challenges. Challenge 1. Requires a running Vespa instance. Vespa Store relies on a running Vespa instance, which might require additional infrastructure setup and maintenance. This could pose a challenge for users without existing Vespa installations, as they need to set up and manage a separate infrastructure component. Challenge 2. Potentially complex to configure and maintain. Configuring and maintaining a Vespa instance can be complex, potentially requiring advanced technical knowledge. Users need to be familiar with Vespa's configuration options and have the necessary skills to manage its operation, potentially requiring a steeper learning curve compared to other vector stores. Zep Vector Store. A description of Zep Vector Store: a langchain community vector store for Zep.ai. Langchain community vector store for Zep.ai. Components. Component 1. Zep.ai description. Zep.ai is a platform that provides a powerful embedding model for representing text data in a numerical format. It enables efficient search and retrieval of information based on semantic similarity. Component 2. Langchain description. Langchain is an open-source framework for building and deploying language models in real-world applications. It offers a variety of tools and components for managing, querying, and interacting with language models, including vector stores for embedding data. Component 3. Vector store description. A vector store is a data structure that stores and retrieves embeddings efficiently. It allows you to find semantically similar items based on their vector representations. Architecture is based on LangChain's vector store interface and Zep.is application programming interface. A LangChain vector store for storing and retrieving embeddings from Zep.ai. It acts as a bridge between LangChain's functionality and Zep.is embedding capabilities, enabling seamless integration for tasks such as semantic search, question answering, and information retrieval. Leverages Zep.ai's powerful embedding model description by utilizing Zep.is advanced embedding model. The Zep vector store benefits from high-quality vector representations, leading to improved search results and enhanced semantic understanding of data. Easy integration with LangChain description. Zep vector store is designed to seamlessly integrate with LangChain's ecosystem, making it easy to incorporate into existing langchain workflows and applications. Potential performance issues with large datasets. Description. When dealing with large datasets, the performance of retrieving embeddings from zep.is.p may become a bottleneck. Optimizations and caching strategies might be required to mitigate this. May require familiarity with both langchain and zep.ai. Description. Users may need to have a basic understanding of both langchain and zep.ai to effectively utilize and configure Zep Vector Store, as it requires knowledge of both frameworks and their functionalities. Langchain Community Vector Stores. Yellowbrick Summary. None. Langchain Community's Yellowbrick Vector Store is a custom vector store built upon the Yellowbrick database, combining the capabilities of vector search with the efficiency and scalability of Yellowbrick. Component 1. Langchain refers to the open source library that offers a framework for building applications powered by large language models (LLMs). It offers tools and techniques for tasks such as question answering, text summarization, and document search. Component 2. Yellowbrick is a high-performance, distributed database designed for analytical workloads. It excels in efficiently storing and retrieving large datasets, including vector embeddings. It leverages Yellowbrick's capabilities for storing and retrieving vector embeddings, allowing for efficient similarity search and retrieval of relevant information. This vector store provides an efficient way to store and query vector embeddings, enabling users to leverage langchain for various natural language processing tasks, including question answering, text summarization, and document search. Advantage 1. Scalability refers to the ability of the vector store to handle increasing amounts of data and queries without significant performance degradation. This is essential for applications that deal with large volumes of text and require fast responses. For example, a search engine for a large online library would need a highly scalable vector store to handle a massive number of documents and queries. Advantage 2.
Efficiency means that the vector store can perform searches and retrievals quickly and effectively. This is crucial for user experience, as users expect search results to be returned promptly. For instance, a chatbot that uses a vector store to understand user queries would need an efficient store to provide quick and accurate responses.
Challenge 1. Limited community support means that there may be fewer resources and help available compared to other vector stores. This can be a challenge for developers who encounter issues or need guidance, potentially increasing the time and effort required to troubleshoot and solve problems. Challenge 2. Potentially higher learning curve suggests that the vector store might require more effort to learn and use effectively. This can be due to its complex architecture, specialized features, or specific configuration requirements. For example, a developer new to distributed databases might find it challenging to set up and manage the Yellowbrick Vector Store. Langchain Community Vector Stores. Alibaba Cloud OpenSearch. Create metadata. None. This section provides a detailed explanation of the Langchain Community Vector Stores, Alibaba Cloud OpenSearch. Create metadata concept. The concept is composed of various components that contribute to its overall functionality. Components. Component 1. This component refers to the integration of Langchain Community Vector Stores with Alibaba Cloud OpenSearch. Langchain is a framework that provides tools and libraries for building and deploying language models, LLMs, and other AI applications. Vector stores are used to store and retrieve vectors, which are mathematical representations of data. Alibaba Cloud OpenSearch is a fully managed Elasticsearch service offered by Alibaba Cloud. This integration allows users to utilize LangChain's vector store capabilities within the Alibaba Cloud Open Search environment. Component 2. This component describes the process of creating metadata for Alibaba Cloud Open Search. Metadata is essential for organizing and managing vector data stored within the Open Search Index. It provides information about the vectors, such as their dimensionality, data type, and any relevant tags or labels. This metadata facilitates efficient querying and retrieval of vector data from Alibaba Cloud Open Search. This section describes the architectural foundation supporting the LangChain community vector stores. Alibaba Cloud Open Search create metadata concept. The architecture outlines the components involved, their interactions, and the overall design principles. Role. This section explains the role of LangChain community vector stores. Alibaba Cloud Open Search create metadata within a broader system. It clarifies how this concept fits into the overall workflow and contributes to the system's functionality. Advantages. Advantage 1. A key advantage of this integration is the ability to perform efficient querying of vector data stored within Alibaba Cloud Open Search. Vector data, often used in semantic search and recommendation systems, can be queried based on similarity rather than exact keyword matching. This enables users to retrieve relevant results even if their search query does not perfectly match the stored data. For example, a user searching for information about artificial intelligence might retrieve documents related to machine learning, deep learning, or natural language processing, thanks to the similarity-based search capabilities of vector data. Advantage 2. Another advantage is the improvement in retrieval accuracy achieved by leveraging vector similarity. Search capabilities. Vector search algorithms can identify and retrieve similar vectors based on their proximity in a multidimensional space. This approach can significantly enhance the accuracy of search results compared to traditional keyword-based search methods. For instance, a user searching for recipes using chicken and vegetables might retrieve recipes that use ingredients like broccoli, carrots, and potatoes even though these specific ingredients were not explicitly mentioned in the search query. Challenge 1. Ensuring proper configuration of the Alibaba Cloud Open Search Index and metadata is a critical challenge. The index structure and metadata definition need to be designed carefully to optimize storage efficiency and query performance. Incorrect configuration can lead to performance bottlenecks and inaccurate search results. Challenge 2. Optimizing search performance by considering vector dimensionality and indexing strategy is another key challenge. The dimensionality of vectors, which represents the number of features used to describe them, can significantly impact search performance. High-dimensional vectors often require more computational resources for indexing and querying. Selecting an appropriate indexing strategy, such as using inverted indices or approximate nearest neighbor search algorithms, can help mitigate the impact of high dimensionality and improve search performance. Furthermore, choosing an indexing strategy that balances accuracy and efficiency is crucial. For example, using an approximate nearest neighbor search algorithm can provide faster results but may sacrifice some accuracy compared to a brute force search. LangChain Community Vector Stores ClickHouse has mul sub str. None. Detailed definition of the variable goes here. Components. Component 1. ClickHouse is a column-oriented database that is optimized for analytical workloads. It is designed to handle large amounts of data and perform complex queries efficiently. For example, it can be used to analyze web server logs, customer data, or financial transactions. Component 2. LangChain is a framework for building applications that use large language models. It provides a set of tools and libraries that make it easy to integrate LLMs into your applications. For example, you can use LangChain to build a chatbot, a question answering system, or a content generator. Component 3. Vector stores are used to store and retrieve embeddings. Embeddings are numerical representations of text or other data that can be used to measure the similarity between different pieces of data. For example, you can use a vector store to find documents that are similar to a given query. Component 4. Hasmul substr is a function that searches for multiple substrings in a string. It returns true if all of the substrings are found in the string and false otherwise. For example, you can use Hasmul substr to check if a string contains all of the keywords in a search query. Description of the architecture supporting the variable. ClickHouse database is used to store embeddings. LangChain is used to interact with the database. The embeddings are stored in ClickHouse as vectors. And LangChain can use the Hasmul substr function to search for embeddings that are relevant to a given query. Explanation of the variable s role in the system. Hasmul substr is used to search for multiple substrings in a string in the ClickHouse database. This is used to find embeddings that are relevant to a query. For example, if a user searches for a document about machine learning, the Hasmul substr function can be used to find embeddings that contain the substrings machine and learning. ClickHouse is a fast and efficient database. It can handle large amounts of data and perform complex queries quickly. This makes it a good choice for applications that require real-time analytics. Hasmul substr is an efficient function that searches for multiple substrings in a string. It can quickly find all of the substrings that are present in a string. This makes it a good choice for applications that need to perform large numbers of searches. ClickHouse can be difficult to set up and configure. It requires a good understanding of database administration and tuning. Hasmul substr can be difficult to use for complex queries. It can be difficult to write queries that search for multiple substrings in a string in a way that is efficient and accurate. Ensuring data consistency between ClickHouse and LangChain is essential for maintaining data integrity and accuracy when data is transferred between these two components. It is crucial to ensure that the data remains consistent and free from errors. This can be challenging due to the different data models and storage mechanisms used by ClickHouse and LangChain strategies for maintaining data consistency may include data validation techniques and using consistent data formats across the system. Challenge 2. Optimizing query performance for large datasets is a key challenge in this context. As the amount of text data grows, it becomes increasingly important to ensure that queries can be executed efficiently and without significant delays. This requires optimizing query plans using appropriate indexes and taking advantage of ClickHouse's powerful query optimization capabilities. Strategies may also include data partitioning and sharding techniques to distribute data across multiple nodes and improve query performance. LangChain Community Vector Stores. ClickHouse Hasmul substr. None. Detailed definition of the variable goes here. Components. Component 1. ClickHouse is a column-oriented database management system. ClickHouse stores data in columns instead of rows, which optimizes query performance for analytical workloads. It is widely used for real-time analytics, data warehousing, and time series analysis due to its high speed and efficiency in handling large datasets. Component 2. It is known for its high performance and scalability. ClickHouse excels in handling massive data volumes with rapid query execution. This performance is achieved through its columnar storage format and efficient query processing engine. ClickHouse can scale horizontally by adding more nodes to a cluster, distributing the workload across multiple servers, and providing a robust and scalable solution for data-intensive applications. Component 3 LangChain is a framework for building and deploying language models. LangChain provides a comprehensive toolkit for developers to integrate large language models (LLMs) into various applications. It offers a modular and flexible architecture, enabling users to easily connect LLMs with data sources, APIs, and other tools. LangChain facilitates the creation of powerful and customized AI applications by streamlining the process of interacting with and harnessing the capabilities of LLMs. Component 4 LangChain Community Vector Stores. ClickHouse Hasmul Sub-STR is a vector store implementation that uses ClickHouse as its underlying database. This implementation leverages the capabilities of ClickHouse to provide a performant and scalable solution for storing and retrieving vector embeddings. It allows users to store and manage embeddings efficiently, enabling advanced functionalities like similarity search and retrieval. Component 5 This vector store implementation leverages the capabilities of ClickHouse to provide high performance and scalability for storing and retrieving embeddings. ClickHouse's columnar storage format and efficient query processing engine optimize the storage and retrieval of vector embeddings. This enables the vector store to handle large datasets with speed and efficiency, making it suitable for applications requiring fast and accurate vector search. Description of the architecture supporting the variable. ClickHouse stores embeddings as a vector of numbers. These vectors represent the numerical representation of data points, capturing their semantic relationships. Each embedding is stored as a series of numbers, and ClickHouse provides efficient methods to manage and search for these vectors. It provides an efficient way to search for similar embeddings. ClickHouse facilitates similarity search by utilizing distance metrics to calculate the similarity between vectors. By calculating the distance between vectors, it identifies embeddings that are close to each other in the embedding space, indicating that they represent similar concepts or entities. This is done by using a distance metric to calculate the similarity between vectors. Various distance metrics are available, such as Euclidean distance and cosine similarity, which measure the dissimilarity and similarity between vectors, respectively. The choice of metric depends on the nature of the embeddings and the specific use case. The similarity is calculated based on the distance between the vectors. By comparing the distances between vectors, ClickHouse determines the level of similarity between them. Vectors with smaller distances are considered more similar, while vectors with larger distances are considered less similar. Vectors closer to each other in the embedding space are considered more similar. In the embedding space, vectors representing related concepts are located close to each other. The similarity between vectors is determined by their proximity in this space. This approach allows for fast and efficient retrieval of similar embeddings based on the provided query. When a query is submitted, ClickHouse calculates the distance between the query vector and all stored embeddings by ranking the embeddings based on their distance to the query vector. It efficiently retrieves similar embeddings, providing relevant and meaningful results. Explanation of the variable's role in the system. LangChain Community Vector Stores. ClickHouse Hasmul Sub-STR allows users to leverage the power of ClickHouse for storing and retrieving embeddings. By integrating ClickHouse into LangChain, Users can utilize its capabilities for efficient vector storage and retrieval. This implementation enables powerful functionalities for building applications that require similarity search and embedding management. This implementation enables efficient and scalable vector search, which is crucial for applications that involve similarity search, recommendation systems, and question answering. LangChain Community Vector Stores ClickHouse has Mool Sub-STR provides a robust solution for vector-based applications. Its efficient vector search capabilities are essential for various use cases, including finding similar items in a product catalog, recommending relevant content, and answering questions based on knowledge embedded in vectors. High performance and scalability for storing and retrieving embeddings. ClickHouse's columnar storage format and optimized query processing engine enable high-speed storage and retrieval of embeddings. This allows the vector store to handle large datasets efficiently, ensuring rapid access to embeddings and enabling fast search operations. The scalability of ClickHouse allows the system to handle increasing data volumes and accommodate growing computational demands. Efficient similarity search using ClickHouse's capabilities. ClickHouse provides efficient algorithms for performing similarity search on vector data. It uses indexing techniques and optimized query execution to quickly find similar embeddings based on the provided query vector. This feature enables applications to search for relevant information, identify similar items, and perform other tasks that rely on vector similarity. Robust and reliable data management with ClickHouse. ClickHouse is known for its robustness and reliability. It provides data consistency, fault tolerance, and data integrity features that ensure the safety and accuracy of the stored embeddings. This reliability makes ClickHouse a suitable choice for applications where data integrity and availability are crucial. Limited support for advanced vector search features like approximate nearest neighbor search. While ClickHouse provides efficient vector search capabilities, it may not support advanced features like approximate nearest neighbor search. This feature is crucial for applications requiring highly accurate similarity search on large data sets. Potential performance limitations for very large datasets. Depending on the ClickHouse configuration. For exceptionally large datasets, ClickHouse might experience performance limitations, depending on the system configuration and hardware resources. Optimizing the ClickHouse configuration and ensuring sufficient hardware resources are crucial to maintain high performance for large-scale vector storage and retrieval. Integration complexity with other parts of the LangChain ecosystem, requiring specific configuration and setup. Integrating langchain community vector stores. ClickHouse has Mool Sub-STR with other components of the LangChain ecosystem might require specific configuration and setup, which can add complexity to the integration process. Users need to ensure proper configuration and data mapping to ensure seamless integration and interoperability between different LangChain components. Summary of LangChain Community Vector Stores. Neo4j Vector check if not null. None. Detailed definition of the LangChain Community Vector Stores. Neo4j Vector check if not null. This component represents a specific implementation within the LangChain ecosystem focused on managing vector embeddings using Neo4j's graph database. It combines the capabilities of vector embedding storage with the power of Neo4j's graph database to enable efficient retrieval and analysis of textual data. Components. Component 1. This component is responsible for storing and retrieving embeddings for text data. This component, typically a vector store, acts as an intermediary between the LangChain application and the Neo4j database. It handles the translation of text data into numerical embeddings and vice versa, ensuring seamless communication with the database. For example, a user query will be converted into an embedding by this component before being sent to Neo4j for similarity search. The results retrieved from Neo4j will then be translated back into human-readable text by this component. Component 2. This component is responsible for managing the Neo4j database, which stores the embeddings and their associated metadata. This component handles all interactions with the Neo4j database, including storing and retrieving vector embeddings and their associated metadata. It leverages Neo4j's graph capabilities to create a network of relationships between embeddings, reflecting the semantic relationships between the underlying text data. This allows for more sophisticated search and retrieval operations beyond simple keyword matching. Description of the architecture supporting the langchain community vector stores Neo4j vector check. If not null, this component utilizes Neo4j to store and retrieve text embeddings. The architecture involves a vector store component, a Neo4j database, and a layer of communication that enables the seamless exchange of data between them. This architecture allows for flexible integration with various langchain components and empowers developers to build complex search and retrieval applications. Explanation of the langchain community vector stores Neo4j vector check if not null role in pay system. This component is a crucial part of the langchain ecosystem, enabling efficient and scalable text retrieval and search. This component significantly enhances the capabilities of langchain by providing a specialized mechanism for managing vector embeddings using the powerful Neo4j graph database. This allows langchain applications to perform sophisticated semantic search and retrieval operations, making it possible to handle large datasets of text data efficiently and retrieve relevant information with high accuracy. Allows for efficient and scalable storage and retrieval of text embeddings using Neo4j's graph database capabilities. This component leverages Neo4j's advanced graph database features, enabling efficient storage and retrieval of large volumes of vector embeddings. This scalability is crucial for handling complex datasets and performing real-time searches. For example, a news organization could use this component to store and retrieve embeddings for millions of articles, enabling users to perform semantic searches and retrieve relevant articles based on their content. Offers flexibility and customization in defining relationships between embeddings based on their content and similarity. Neo4j's graph database allows for flexible and customizable relationships between embeddings, reflecting the semantic relationships between the underlying text data. This enables more sophisticated search queries and retrieval of data based on complex criteria. For instance, a research team could use this component to store and analyze a corpus of scientific articles, defining relationships between articles based on their citations, shared keywords, or other relevant factors. Efficiently handling large datasets of embeddings can be challenging, requiring optimization of indexing and query strategies. Managing large datasets of embeddings within a Neo4j database can be complex, requiring careful planning and optimization of indexing and query strategies to ensure efficient performance. This includes choosing appropriate index structures, optimizing queries, and potentially implementing techniques like data partitioning to handle large datasets. Maintaining data consistency and integrity across multiple nodes in a distributed Neo4j deployment can be complex. Deploying Neo4j in a distributed environment can introduce challenges in maintaining data consistency and integrity across multiple nodes. This requires careful planning and implementation of mechanisms for data replication, synchronization, and conflict resolution to ensure a reliable and consistent data store. Langchain Community Vector Stores Neo4j Vector Combine Queries. A detailed explanation of the langchain community vector stores Neo4j Vector Combine Queries, including its definition, architecture, role, advantages, and challenges. Detailed definition of the variable goes here. Components. Component 1. Langchain's Neo4j Vector Store is a component that enables the storage and retrieval of data using vector embedding. Langchain is an open-source framework for building and deploying large language model applications. Neo4j is a graph database that provides a flexible and scalable way to store and query interconnected data. Vector embedding is a technique used to represent data as numerical vectors in a high-dimensional space. By storing data as vectors, Langchain's Neo4j Vector Store allows for efficient similarity search and retrieval based on semantic relationships between data points. Component 2. The Combine Queries feature is a crucial aspect of the system. It enables the merging of multiple search queries into a single, comprehensive query. This aggregation of queries enhances the accuracy and relevance of the search results, making the retrieval process more efficient and effective. Description of the architecture supporting the variable. The architecture supporting Langchain Community Vector Stores Neo4j Vector Combine Queries relies on a graph database. Neo4j. The graph database structure is particularly suitable for storing information about vectors and relationships between them. In essence, each vector is represented as a node in the graph, and the relationships between these vectors are defined by edges connecting them. This structure allows for efficient navigation and retrieval of information based on relationships between vectors. Explanation of the variable's role in the system. The primary role of Langchain Community Vector Stores Neo4j Vector Combine Queries is to facilitate efficient and flexible information retrieval and knowledge discovery. By leveraging vector embeddings, the system enables searches based on semantic meaning rather than exact keyword matching. This semantic understanding of data allows for more accurate and relevant search results. Moreover, the use of a graph database enhances the ability to discover complex relationships between data points, ultimately leading to a richer and more comprehensive understanding of the information stored within the system. The system offers significant advantages in terms of enhanced search accuracy and relevance. By understanding the semantic relationships between data points through vector embedding, the system can identify relevant information that might be missed by keyword-based searches. This improvement in search accuracy leads to more relevant and meaningful results for users. The Langchain Community Vector Stores Neo4j Vector Combine Queries system also contributes to an improved user experience. The ability to combine multiple search queries into a single comprehensive query simplifies the search process for users. Additionally, the semantic search capabilities make it easier for users to find relevant information without having to precisely match keywords. This streamlined and intuitive search process enhances user satisfaction and makes the system more accessible. Managing and updating vector representations is one of the key challenges in maintaining an effective Langchain Community Vector Stores Neo4j Vector Combine Queries system. As new data is introduced, it is crucial to ensure that the vector representations are updated accurately to reflect the evolving information landscape. This process involves continuously evaluating and refining the vector representations to maintain consistency and accuracy. Ensuring scalability and performance of the vector store is another critical challenge. The system must be able to handle large volumes of data while maintaining high performance and responsiveness. Scaling the vector store infrastructure is essential to accommodate growing data volumes and user demands. Moreover, optimizing the search and retrieval algorithms is critical to ensure that the system can efficiently process queries and deliver results in a timely manner. Langchain Community Vector Stores ZEP Collection Config Summary. NaN. A collection config defines the configuration for a ZEP collection. This configuration serves as a blueprint for how ZEP will manage and process data. It determines the storage format, how data is split into chunks, and how similarity calculations are performed. Component 1. Collection name. A unique identifier for the collection. This name helps differentiate between different data sets that might be managed by ZEP, such as a collection of scientific articles or a collection of customer support tickets. Embedding function. The specific mathematical function used to transform text documents into numerical vectors. This function helps ZEP understand the meaning of the text by capturing its semantic relationships. For example, a popular choice is the OpenAI Embeddings API, which produces vectors that are well suited for various natural language tasks. Similarity function. The algorithm used to calculate the similarity between two vectors. This function is critical for finding documents that are semantically close, even if they don't share the same words. A common choice is cosine similarity, which measures the angle between two vectors. Vector store. The system used for storing and retrieving the numerical vectors representing the documents. Popular choices include FICE, a library optimized for efficient search in large datasets, and Milvus, a cloud-based vector database designed for scalability. Chunk size. The number of words or characters used to split a document into smaller chunks. Chunking is essential for processing large documents efficiently, as it allows ZEP to work with smaller, manageable units of text. Chunk overlap. The amount of overlap between two adjacent chunks. This overlap helps prevent information loss at the boundaries of chunks, ensuring that the semantic context of a document is preserved. Metadata field. A specific field in the document that stores additional information, such as the author, publication date, or topic. This metadata can be used for filtering or sorting the results of a search. ZEP collections are built on top of the Zilli vector database. Zilli is a powerful and efficient vector database that provides the foundation for storing and retrieving the embeddings generated by ZEP. This database is optimized for search performance and scalability, making it suitable for handling large datasets. Provides a consistent way to configure and interact with ZEP collections. This configuration helps standardize how ZEP collections are managed and accessed, ensuring consistency across different projects and applications. It offers a defined interface for interacting with the ZEP collection, facilitating efficient data processing and retrieval. Provides a standardized way to configure ZEP collections. This standardization ensures that all ZEP collections adhere to a common framework, promoting interoperability and ease of use. Developers and users can rely on a consistent structure, making it simpler to manage and access data across different collections. Enables easy integration with different vector stores and embedding functions. ZEP collections can be configured to work with various vector stores and embedding functions, providing flexibility and adaptability to different use cases. This allows users to choose the best suited tools for their specific needs. enhancing the overall efficiency and performance of the system. Requires understanding of ZILI and ZEP concepts. Utilizing ZEP effectively necessitates familiarity with the concepts underlying ZILI and ZEP. This includes understanding the core principles of vector databases, embedding functions, and search strategies. Can be complex to configure for advanced use cases. Advanced use cases may require intricate configurations to fine-tune ZEP's behavior and performance. This can involve understanding specific parameters, optimizing data splitting strategies, and selecting appropriate vector similarity metrics. Langchain Community Vector Stores LancedB Import LancedDB. This is a description of langchain community vector stores LancedB Import LancedDB. It explains the purpose, components, architecture, role, advantages, and challenges associated with this feature. Detailed definition of the variable goes here. Components. Component 1. LangChain is an open source framework that enables developers to build and deploy applications. Powered by large language models (LLMs), it provides a unified interface for interacting with LLMs, along with tools and components for building various LLM-powered applications. Component 2. Vector stores are databases that store and retrieve data based on semantic similarity. They are commonly used in applications that involve natural language understanding, search, and recommendation. Vector stores represent data points as vectors in a high-dimensional space, where similar data points are close to each other. Component 3. LancedB is an open-source, high-performance database optimized for storing and querying large datasets of vector embeddings. It is built on Apache Arrow and uses a columnar storage format for efficient data retrieval. LancedB is particularly well suited for applications that require fast search and retrieval of similar vectors, such as recommendation systems and search engines. Component 4. Import LancedDB is a method used to load data from a LancedDB file into a vector store. It provides a convenient way to leverage the performance and scalability of LancedDB for storing and retrieving vector embeddings. Architecture. Description of the architecture supporting the variable. Role. Explanation of the variable's role in the system. Advantages. Advantage 1. Efficient data loading. LancedDB's columnar storage format and optimized query engine allow for fast data retrieval, making it efficient to load large datasets into a vector store. Advantage 2. Supports large datasets. LancedDB is designed to handle large datasets, making it suitable for applications that require storing and retrieving large amounts of vector data. Challenges. Challenge 1. Requires LancedDB installation. To use Import LancedDB, you need to have LancedDB installed and configured on your system. Challenge 2. Limited to LancedDB data format. Import LancedDB is specifically designed for loading data from LancedDB files, limiting its applicability to other data formats. Challenge 3. Potential performance issues for large datasets. While LancedDB is designed for large datasets, performance can be impacted by factors such as the size and complexity of the data, as well as the hardware resources available. LangChain Community Vector Stores Neo4j Vector Remove Leucine chars. Definition. This variable is used to clean up the text before it is indexed in the Neo4j database. It removes any characters that are considered special by Leucine, such as white space, punctuation, and control characters. This ensures that the text is properly indexed and can be searched efficiently. For example, if a text contains a comma or period, Leucine might interpret it as a delimiter and split the text into multiple tokens. This can lead to problems with search results. as the search engine might not be able to find the correct text. By removing these special characters, we ensure that the text is indexed as a single unit, which makes it easier for the search engine to find the correct text. Components. Component 1. A Neo4j vector store is a database that stores vectors, which are mathematical representations of data. It uses the Neo4j graph database to store the vectors and the relationships between them. It enables you to store and search large amounts of data in a fast and efficient manner. For example, you can store vectors representing product descriptions, news articles, or scientific papers. This enables you to search for similar documents or find relationships between them. Component 2. A Neo4j database is a graph database that stores data in the form of nodes and relationships. It is designed to handle complex data structures, such as those found in social networks or financial systems. It is very efficient at finding connections between data points, making it a good choice for tasks like fraud detection or recommendation systems. For example, a Neo4j database could be used to store information about customers, products, and purchasers. This would allow you to quickly find all customers who have purchased a particular product or to identify customers who are likely to be interested in a new product. Architecture. This variable is a simple function that takes a string as input and returns a cleaned UP string as output. The function uses the remove leucine chars function from the langchain community, vectorstores.neo4j vector module to remove any special characters. For example, if you input the string "this is a string with commas, periods, and other special characters," the function will return the string "this is a string with commas, periods, and other special characters." This ensures that the text is properly indexed and can be searched efficiently. Role. This variable is used to clean up the text before it is indexed in the Neo4j database. This ensures that the text is properly indexed and can be searched efficiently. For example, if you are indexing a document that contains a lot of punctuation, it is important to remove this punctuation before indexing. This will ensure that the text is properly indexed and can be searched efficiently. Advantages. Advantage 1. Improved search performance by removing special characters. The search engine can process the text more efficiently, which leads to faster search results. For example, if you are searching for a document that contains the word apple, the search engine will be able to find the document more quickly if it does not have to process any special characters. Advantage 2. Reduced indexing errors. Special characters can sometimes cause indexing errors. By removing these characters, you can reduce the number of indexing errors, which will make your database more reliable. For example, if you are indexing a document that contains a lot of punctuation, it is important to remove this punctuation before indexing. This will ensure that the text is properly indexed and can be searched efficiently. Challenges. Challenge 1. May remove some valid characters, such as commas and periods. It is important to consider the specific use case and choose the appropriate characters to remove. For example, if you are indexing a document that contains a lot of punctuation, it is important to remove this punctuation before indexing. This will ensure that the text is properly indexed and can be searched efficiently. Challenge 2. May not be necessary for all use cases. If you are indexing text that does not contain any special characters, you can skip this step. For example, if you are indexing a document that contains a lot of punctuation, it is important to remove this punctuation before indexing. This will ensure that the text is properly indexed and can be searched efficiently. Summarization of langchain community vector stores Neo4j vector dict to YAML str. Nan. The function converts a dictionary to a YAML string. This process involves transforming the key-value pairs within the dictionary into a structured format that adheres to YAML syntax. This conversion enables the storage and retrieval of data in a human-readable and machine-processable manner, suitable for configurations and data exchange. For instance, when storing user preferences or application settings, the function can efficiently serialize the data as YAML, ensuring its integrity and maintainability. Component 1. Langchain Community Vector Stores.neo4j Vector is a vector store implementation within the langchain framework, leveraging Neo4j as the underlying database. This component enables efficient storage and retrieval of vector embeddings, which are mathematical representations of data points within a graph database environment. Neo4j's graph structure facilitates semantic relationships between data points, allowing for more nuanced similarity searches. Component 2. Dict to YAML str. A function designed to transform a dictionary into a YAML string, plays a crucial role in streamlining the process of converting data structures into a YAML-compliant format. Dictionaries, often used to represent key-value pairs, can be easily transformed into a readable YAML string using this function, enhancing the organization and readability of the data. This function is particularly useful in scenarios where data needs to be stored or shared in a structured manner, ensuring compatibility with YAML-based systems and configurations. The architecture of this function is based on a vector store, a data structure optimized for storing and retrieving similar items. Vector stores, like those implemented in langchain, effectively manage vector embeddings by leveraging data structures and algorithms designed for efficient search and retrieval. This architecture empowers the function to handle high-dimensional data and efficiently locate similar items within a vast collection of vector embeddings. The underlying vector store is integral to the function's ability to perform similarity searches and retrieve relevant information from the stored data. This function plays a crucial role in transforming data stored in a dictionary format into a YAML-compatible string. This conversion facilitates the storage and retrieval of data in a structured and human-readable format, ensuring compatibility with YAML-based systems and configurations. It bridges the gap between the dictionary representation of data and the YAML format, providing a seamless transition for data exchange and storage. For instance, when configuring applications or storing user preferences, the function ensures that data is properly formatted and accessible in a YAML-compatible manner. Facilitates serialization for data storage and retrieval. This function enables the efficient serialization of data stored in dictionaries into a YAML string, making it suitable for storage and retrieval in various formats. The YAML representation ensures data integrity and maintainability, allowing for easy access and manipulation. For example, when storing application settings or user preferences, the function can reliably serialize the data into YAML, ensuring its accessibility and consistency across different systems. Improves readability and structure for YAML-based configurations. The function transforms dictionaries into human-readable YAML strings, enhancing the clarity and organization of configurations. This facilitates easier understanding and modification of data structures, particularly in scenarios involving YAML-based configurations, application settings, or user preferences. The improved readability and structure contribute to better maintainability and collaboration among Users and developers. Handling complex data structures within dictionaries. When dealing with dictionaries containing nested structures, arrays, or complex data types, ensuring proper conversion to YAML can pose challenges. The function needs to handle the intricacies of these data structures and accurately translate them into a valid YAML representation, maintaining the original structure and relationships between data elements, ensuring consistent YAML formatting across different dictionaries. Achieving consistent formatting across multiple dictionaries is crucial for maintaining uniformity and readability. The function should implement rules and strategies to ensure that YAML strings generated from different dictionaries adhere to a consistent style and structure, promoting clarity and reducing potential confusion or errors. This can involve defining specific formatting conventions for indentation, spacing, and key-value separation, ensuring a cohesive and well-organized YAML output across various data sources. This variable represents the sorting mechanism for results retrieved from the Neo4j vector store. Using langchain, it defines the criteria used to order the search results, ensuring consistency and predictability in the retrieval process. This mechanism is essential for organizing and managing search results effectively. Advantages: enables consistent and predictable ordering of search results based on the order of the indices in the Neo4j database. This mechanism ensures that search results are consistently ordered according to the index names defined in the Neo4j database, regardless of the query. This predictability enhances the user experience by making results easy to interpret and navigate. Simplifies result management by providing a clear sorting criterion. By using a clear sorting criterion, it simplifies the process of managing search results. Users can easily understand how the results are ordered, making it easier to navigate and find specific information. Offers flexibility in defining search result ordering based on index names. This mechanism allows for flexibility in defining the order of search results by leveraging index names within the Neo4j database. This provides users with the ability to tailor the results to their specific needs and preferences. For instance, users could prioritize results from a specific index by placing it earlier in the index name order. Challenges: limited flexibility. The primary limitation of this sorting mechanism is that it relies solely on index names for ordering. This lack of flexibility means that other criteria, such as relevance scores or timestamps, cannot be used for sorting. Performance implications: sorting large datasets based solely on index names can potentially impact query performance. As the dataset grows, sorting becomes more computationally demanding, potentially leading to slower response times. Challenges: constructing the Neo4j query in a way that is both efficient and expressive can be challenging, especially for complex metadata filters. Building an efficient and expressive Neo4j query requires careful consideration of the metadata properties, their relationships, and the desired filtering logic. The challenge lies in crafting a query that effectively translates complex metadata conditions into the syntax understood by the Neo4j database. This involves balancing the complexity of the query with its execution efficiency. Ensuring that the query is correctly constructed and returns the expected results requires careful testing. Validating the correctness of the constructed query is crucial to ensure that it accurately reflects the desired filtering conditions. This involves thorough testing with diverse metadata scenarios to guarantee that the query returns the intended set of documents. The process requires rigorous validation to ensure that the query accurately translates the user's intent into a functional database query. The architecture of this component involves seamlessly integrating the removal of Lucene characters within the workflow of storing vectors in Neo4j databases. This integration ensures that before any vector data is persisted in Neo4j, any potential Lucene special characters are eliminated. This architectural decision is crucial for maintaining the integrity and consistency of the vector data stored within Neo4j. Role: this component plays a vital role in ensuring the seamless and efficient use of Neo4j databases within the context of langchain vector stores. By removing Lucene special characters before storing vectors in Neo4j, it eliminates potential issues that might arise due to incompatible character sets. This ensures that the vectors are stored consistently, facilitating accurate and efficient querying and retrieval of vector data. Advantages: removing Lucene special characters leads to significant improvements in query performance. By eliminating characters that are not readily handled by Neo4j, the component optimizes the way queries are processed, making them faster and more efficient. This is particularly advantageous in scenarios where fast and accurate retrieval of vector data is crucial. Ensuring consistency in indexing is another key advantage of this component. By removing potential conflicts arising from Lucene special characters, the component ensures that vectors are consistently indexed, facilitating accurate and reliable search results. This consistency is crucial for maintaining the integrity and reliability of the vector data stored within Neo4j databases. Challenges: one challenge associated with this component is the potential for conflicts arising from Lucene special characters during the indexing process. These characters, while essential for Lucene's search capabilities, might not be compatible with the structure or conventions of Neo4j databases. Therefore, removing them becomes essential to avoid potential inconsistencies or errors during indexing. Another challenge might involve making modifications to the indexing pipeline. This could involve updating existing code or scripts used to index vectors in Neo4j databases. These modifications are crucial for seamlessly incorporating the removal of Lucene characters into the existing workflow, ensuring consistent and accurate indexing of vector data in Neo4j databases. Summary of langchain community vector stores Neo4j vector construct metadata filter. None. Detailed definition of the variable goes here. Components. Component 1. Neo4j vector is a vector store implementation for langchain that leverages Neo4j as its backend. A vector store is a data structure that stores and retrieves vectors representing information from documents. Langchain is a framework that enables the creation of applications powered by large language models. Neo4j is a graph database that stores data as nodes and relationships. The Neo4j vector class utilizes Neo4j to store vector representations of documents and their associated metadata. It enables efficient retrieval of documents based on their similarity to a given query vector. Component 2. Construct metadata filter is a method within the Neo4j vector class that helps filter documents based on their metadata. Metadata refers to data that describes the content of a document, such as its author, creation date, or subject. The construct metadata filter method allows users to retrieve documents based on specific criteria within their metadata. For example, a developer might use this method to retrieve all documents written by a specific author or documents related to a particular topic. Description of the architecture supporting the variable. Neo4j is a graph database that stores data in interconnected nodes and relationships. A graph database allows for the representation of data as nodes and relationships. Each node represents an entity, and relationships connect nodes based on various attributes. Neo4j leverages this architecture to efficiently store and retrieve interconnected information. Neo4j Vector utilizes Neo4j's capabilities to store and retrieve documents with associated vectors. The Neo4j Vector class leverages Neo4j's capabilities to store and retrieve documents with associated vectors. Documents are stored as nodes, and their vector representations are stored as properties within the nodes. The relationships between documents can be defined using different types of relationships, such as similar to, related to, or references. The construct metadata filter method utilizes Neo4j's cipher query language to perform filtering operations on metadata associated with documents. Cipher is a query language specifically designed for Neo4j. The construct metadata filter method utilizes cipher queries to retrieve documents based on specific metadata criteria. For example, a user can specify a cipher query to retrieve all documents written by a specific author or all documents published after a certain date. Explanation of the variable S role in the system. The construct metadata filter method is designed to help developers filter documents based on specific criteria within their metadata. The construct metadata filter method enables developers to perform targeted retrieval of documents based on specific metadata attributes. This is useful in scenarios where developers need to retrieve specific subsets of documents based on their characteristics. This method is typically used in scenarios where developers need to retrieve documents that match certain metadata properties or values. For instance, developers might use this method to retrieve all documents written by a specific author, all documents published after a specific date, or all documents related to a particular topic. This method provides a convenient way to filter and retrieve relevant documents based on their metadata, provides efficient filtering based on metadata associated with documents. The construct metadata filter method allows for efficient filtering of documents based on specific metadata properties. This enables developers to quickly retrieve the documents they need based on their metadata characteristics. The efficiency of the filtering process is attributed to the use of Neo4j's cipher query language, which allows for fast and efficient data retrieval. Leverages the graph database capabilities of Neo4j for fast and flexible data access. Neo4j's graph database architecture enables fast and flexible data access. The construct metadata filter method leverages Neo4j's capabilities to perform efficient filtering operations based on metadata associated with documents. The graph database structure allows for flexible relationships between nodes, enabling efficient retrieval of documents based on various metadata criteria. Requires familiarity with Neo4j and cipher query language to effectively utilize metadata filtering capabilities. Effectively utilizing the construct metadata filter method requires understanding the fundamentals of Neo4j and cipher query language. Developers need to learn how to construct cipher queries to specify the desired filtering criteria based on metadata properties. This may require additional learning and effort for developers who are not familiar with graph databases, and cipher may involve complex cipher queries for intricate metadata filtering requirements. For complex metadata filtering scenarios, developers may need to create intricate cipher queries. These queries might involve multiple clauses and conditions to accurately capture the desired filtering criteria. Designing and implementing these complex queries can be challenging and time-consuming. Langchain community vector stores Neo4j vector sort by index name. A detailed analysis, a detailed description. This variable represents a comprehensive analysis of Neo4j vector sort by index name, a feature within the langchain community vector stores ecosystem. Aimed at providing efficient and scalable vector database systems, the variable encompasses two core components: Neo4j vector store implementation, which facilitates the storage and retrieval of vector embeddings within a Neo4j database. Sort by index name, a mechanism for ordering results based on the order of embedding indices within the Neo4j database. This component leverages the power of Neo4j, a graph database renowned for its scalability and efficiency, to create a robust vector database system. The architecture incorporates the Neo4j vector store implementation, enabling the storage and retrieval of vector embeddings, and the sort by index name feature, which facilitates the ordering of results based on the order of embedding indices within the Neo4j database. The role of Neo4j vector sort by index name is paramount in enabling the retrieval of relevant information based on semantic similarity. This is achieved by leveraging vector embeddings, which represent the semantic meaning of data points. The process involves storing and retrieving these embeddings in the Neo4j database, subsequently ordering results based on the embedding index order. This approach allows the system to efficiently identify and retrieve information semantically, similar to a given query. Imagine searching for a recipe for chocolate cake using a recipe search engine powered by this system. The system retrieves the vector embedding for chocolate cake and finds similar recipes based on semantic similarity, such as chocolate brownies or chocolate mousse. The integration of Neo4j, a powerful graph database, provides a significant advantage in terms of data storage and retrieval efficiency. Neo4j's graph database capabilities allow for the creation of complex relationships between data points, enabling faster and more efficient retrieval of relevant information. For example, in a customer relationship management system, Neo4j's graph database can be used to store and retrieve customer interactions, purchase history, and demographic information, allowing for a more comprehensive understanding of customer behavior. A key benefit of Neo4j vector sort by index name is its flexibility and scalability in managing large volumes of vector embeddings. The use of Neo4j as a foundation provides the capacity to handle vast datasets of embeddings efficiently, making it suitable for large-scale machine learning and AI applications. For instance, in a recommendation system powered by this approach, the system can manage a vast database of user preferences and product information, allowing for personalized recommendations based on user behavior and preferences. One challenge in implementing this system is managing the inherent complexity of working with a graph database. Neo4j's graph database model, while powerful, requires a deeper understanding of graph data structures and query languages. This might necessitate specialized expertise in graph database management and query optimization. However, the benefits of using a graph database, such as its efficiency and scalability, outweigh this challenge. Ensuring efficient query processing and retrieval of relevant data is another challenge, as the system needs to handle large volumes of vector embeddings and execute queries efficiently. This requires careful optimization of the query engine and data indexing strategies to minimize query latency and maximize retrieval accuracy. For example, in a search engine using this system, optimizing query processing is crucial for ensuring fast and accurate search results, especially when dealing with large datasets of documents and queries. Evaluates filter expressions to ensure they are correctly formed and do not contain potentially harmful operators. This component inspects incoming filter expressions before they are applied to the vector store. It checks for syntax errors and ensures that the operators used are safe and efficient. The Redis vector store utilizes the Redis database to store embeddings and metadata. The check operator misuse component acts as a filter, inspecting incoming filter expressions before they are applied to the vector store. This architecture allows for efficient filtering and prevents malicious or inefficient filter expressions from being applied to the vector store. This code plays a crucial role in maintaining performance and security by preventing malicious or inefficient filter expressions from being applied to the vector store. For example, an attacker could craft a filter expression that would cause the Redis server to perform a large number of operations, slowing down the application or even crashing the server. By preventing such attacks, this code helps to ensure that the vector store is safe and efficient. Enhanced performance optimized filtering by preventing inefficient or incorrect expressions. By preventing inefficient or incorrect filter expressions, this code can significantly improve the performance of the vector store. For example, if a filter expression uses an operator that is known to be inefficient, this code can prevent it from being executed, thereby improving the overall performance of the vector store. Improved security reduced risk of malicious or unintended filter expressions compromising a database. By preventing malicious or unintended filter expressions, this code helps to improve the security of the vector store. For example, an attacker could craft a filter expression that would allow them to access sensitive data stored in the vector store. This code helps to prevent such attacks by ensuring that all filter expressions are safe and secure. Potential for false positives. Strict filtering rules might mistakenly flag valid expressions, requiring adjustments to the filter logic. This challenge arises because the filter logic needs to be strict enough to prevent malicious expressions but not so strict that it blocks valid expressions. This can be addressed by carefully designing the filtering rules and testing them thoroughly. Limited operator support. Restricting operators can limit the expressiveness of filters, making it challenging to represent complex search queries. This can be addressed by carefully choosing the set of supported operators and ensuring that they provide a sufficient range of functionality. For example, the set of supported operators should be sufficient to allow users to perform common search operations, such as filtering by keywords, dates, and locations. Refined filter rules refine the filter logic to minimize false positives while still ensuring security and performance. This can be achieved by carefully evaluating the filter logic and making adjustments to minimize the number of false positives. The goal is to strike a balance between security and performance. Expand supported operators. Extend the supported operators set to allow for a broader range of filter expressions while maintaining safety. This can be achieved by carefully evaluating the set of supported operators and adding new operators that are both safe and useful. For example, the set of supported operators could be extended to include operators that allow users to perform more complex search operations, such as filtering by ranges or using fuzzy matching. Challenges. Synchronous calls can impact performance, potentially slowing down retrieval processes. Synchronous calls block the execution thread until a response is received from the quadrant database. This can slow down the retrieval process, especially when dealing with large datasets or a high volume of requests. In such scenarios, asynchronous calls can provide better performance by allowing other tasks to execute while waiting for responses from the database. May not be ideal for large datasets or real-time applications requiring fast response times. Synchronous calls can be inefficient for large datasets or real-time applications where fast response times are crucial. In these scenarios, asynchronous calls are often preferred as they allow the application to continue processing other tasks while waiting for responses from the quadrant database. This approach can significantly improve performance and responsiveness, especially when dealing with a high volume of data. Summary of langchain community vector stores. Redis-based check index exists. Description of the YAML content. This YAML file provides a comprehensive overview of the check index exists function within Pay langchain community's Redis-based vector store. It details the function's purpose, underlying architecture, benefits, and potential challenges. Definition of check index exists. Components. Component 1. Checks if an index already exists in the Redis database. Component 2. This check is crucial for efficient vector store management, allowing the system to either create a new index or load an existing one based on the outcome of the check. Architecture of check index exists. Redis is the chosen backend storage solution for the vector store, serving as the foundation for data persistence and retrieval. Role of check index exists. The check index exists function ensures that interactions between the vector store and Redis are both secure and optimized. Advantages of check index exists. By verifying the presence of an index before attempting to create one, the function prevents the unnecessary creation of redundant indices, thereby conserving resources and enhancing performance. The function plays a critical role in preventing data corruption by ensuring that only one index is associated with a particular dataset. This is especially important in scenarios where data might be updated or modified, as it guarantees data consistency and integrity. Challenges of check index exists. The function requires an active connection to a Redis instance for successful operation. In situations where the Redis instance experiences performance bottlenecks or latency issues, this can potentially introduce delays in the execution of the check index exists function, impacting overall system responsiveness. Real-world example of check index exists. Imagine a scenario where a vector store is being used to manage a large dataset of customer reviews. When a new review is added, the check index exists function is called to determine if an index already exists for that specific dataset. If an index already exists, it can be directly loaded and used for efficient search and retrieval of relevant reviews. If no index exists, a new index is created based on the new review data, ensuring that the vector store can effectively handle the expanded dataset. Langchain Community Vector Stores Oracle vs Drop Table Purge Summarization. None. Detailed definition of the variable goes here. Components. Component 1. Oracle VS is a vector store implementation that utilizes Oracle database as the underlying storage mechanism. It provides an interface for storing and retrieving vector representations of data in a structured manner within the Oracle database environment. Component 2. The drop table purge method is a function within the Oracle VS class designed to completely remove the table associated with the vector store from the database. This method effectively erases all data stored within the vector store and removes the underlying table from the database. Description of the architecture supporting the variable. The Oracle VS Vector Store leverages Oracle Database as its storage backend. The drop table purge function interacts directly with the database to execute the deletion operation. This architecture ensures that data is stored securely and efficiently within the Oracle database, with the drop table purge method providing a way to completely remove the data and associated table. Explanation of the variable's role in the system. The drop table purge method serves to permanently delete the underlying table used by the Oracle VS Vector Store, effectively removing all associated data. This method is crucial for managing data within the Oracle VS Vector Store, allowing users to completely remove data when necessary. Complete data removal ensures that all data associated with the vector store is permanently deleted. This ensures that sensitive or outdated information is completely removed from the database, enhancing security and data management practices. For example, if a vector store contains personal information, the drop table purge method can be used to remove this information completely, protecting user privacy. Database efficiency efficiently removes the table from the database, potentially freeing up storage space. By removing the table associated with the vector store, the database can reclaim storage space, improving overall database performance. This is particularly beneficial when dealing with large datasets, as it allows for efficient storage utilization and avoids unnecessary resource consumption. Data loss: irreversible deletion of the vector store's data. This is a significant challenge as it means that once the data is deleted, it cannot be retrieved. It's crucial to have a clear understanding of the data being stored in the vector store and to ensure that all necessary backups are in place before using the drop table purge method. Database impact: potential performance impact on the database during the deletion operation. The deletion operation can impact database performance, particularly for large tables or during peak database usage times. To mitigate this, it's advisable to perform the deletion operation during off-peak hours or after a thorough assessment of potential performance impacts. Challenges: complexity of implementation requires careful consideration of data structures, algorithms, and performance optimizations. Implementing a sort by index name feature for a vector search requires careful consideration of various aspects, including the choice of data structures, the design of algorithms for sorting, and the optimization of query performance. Performance issues can arise, especially with large datasets. Sorting large datasets can impact query performance. This is because the sorting algorithm requires additional processing time and resources to organize the data. However, careful optimization of the sorting algorithm and the use of appropriate indexing techniques can help mitigate these performance issues and ensure efficient retrieval of information even with large datasets. Langchain community vector stores scan: dependable scan import. Elaborated description of each component and their interactions. A mechanism to import data into the scan vector store in a reliable manner. It ensures data integrity by employing the dependable scan import function, which guarantees accurate import even if the process is interrupted. Real-world example: imagine uploading a large dataset of customer reviews into a scan vector store for similarity search. Using the dependable import function, we can be confident that all the data is accurately ingested despite potential network hiccups or system crashes. Component 1. The dependable scan import function is a core component of the scan dependable scan import mechanism. It orchestrates the data import process, utilizing robust error handling and checkpointing to ensure data integrity even during interruptions. Component 2. The scan vector store acts as the destination for the imported data. It is a high-performance vector database designed for efficient similarity search. The scan vector store leverages approximate nearest neighbor search algorithms to quickly retrieve data points that are most similar to a given query vector. The dependable scan import function leverages the scan vector store's capabilities to ensure reliable data import. It employs a series of steps, including data validation, chunking, and error handling, to guarantee data integrity throughout the import process. The function utilizes checkpoints to track the import progress, allowing it to resume from the last checkpoint in case of interruptions, ensuring data consistency and minimizing data loss. The dependable scan import mechanism enables the creation and maintenance of reliable scan vector stores. It provides a robust way to import data, reducing the risk of errors and data loss. This reliability is crucial for downstream tasks that rely on the vector store, such as information retrieval, recommendation systems, and anomaly detection. Advantage 1. Improved data integrity is one of the key advantages of using the dependable scan import mechanism. It ensures that all imported data is accurate and complete, reducing the risk of errors or inconsistencies that can impact downstream tasks. Advantage 2. Increased reliability of vector store creation is another major benefit. The mechanism guarantees data consistency and robustness, making the vector store a reliable foundation for downstream applications. Challenge 1. Interruptions during the import process can occur due to factors like network instability, system crashes, or power outages. The dependable scan import mechanism addresses this challenge by utilizing checkpoints to track the progress and resume the import from the last successful checkpoint, minimizing data loss. Challenge 2. Ensuring data consistency and accuracy is paramount for reliable vector store creation. The dependable scan import function employs strict data validation and error handling to ensure data integrity and consistency throughout the import process. This includes verifying the format, completeness, and correctness of the imported data, ensuring that the vector store contains accurate and reliable information. Challenges. Debugging information can be complex and difficult to understand. The langchain community vector store's *rocks debug output summary variables output can be intricate and require a deep understanding of the *rocks database internals and the vector store's implementation. Developers may need specialized knowledge to interpret the information effectively and use it to pinpoint the root cause of problems. May require familiarity with *rocks database internals. Effectively using the debugging information provided by the langchain community vector stores. *rocks debug output summary variable often requires a good understanding of the *rocks database internals, including its data structures, query processing logic, and performance characteristics. Without this knowledge, developers may find it difficult to interpret the debugging output and leverage it to resolve issues related to the *rocks vector store. Langchain community vector store's *rocks get named result. Detailed definition of the function. Detailed definition of the variable goes here. Components. Component 1. Langchain's *rocks vector store leverages *rocks, a high-performance analytical database, for embedding storage and similarity search. Component 2. The getNamedResult function retrieves documents matching a specific name from the *rocks vector store. Architecture supporting the function. Description of the architecture supporting the variable. The *rocks vector store utilizes *rocks columnar storage and distributed architecture for efficient data retrieval and query execution. Role of the function in the system. Explanation of the variable's role in the system. This method allows users to fetch specific documents based on their predefined names, enabling targeted retrieval from the vector database. Advantages of the function. Efficient retrieval. Star-Rock's columnar storage and distributed architecture enable fast retrieval of documents by name. For example, in a large-scale customer service application, retrieving specific customer records by name can be done efficiently using this function. Scalability. The Star-Rock's vector store can handle large datasets and support multiple concurrent requests. This is beneficial in scenarios involving large-scale e-commerce platforms where numerous users are simultaneously searching for products, ensuring fast response times. Challenges of the function. Limited functionality compared to other vector stores. The Star-Rock's vector store has a more limited feature set. For instance, it may not support advanced search features like semantic search or faceted search, which could limit its application in certain use cases. Star-Rock's dependency requires a Star-Rock's installation, which may involve additional setup and maintenance. This could pose a barrier for users who are not familiar with Star-Rock's or lack the resources for its deployment. LangChain Community Vector Stores. TileDB. Dependable TileDB import. A deep dive. Elaborated description. Detailed definition of the variable goes here. Components. Component 1. TileDB is a highly performant vector store capable of handling large datasets, and it offers a range of features, including indexing, querying, and analytics. TileDB provides a high-performance storage engine specifically designed for vector data. It offers a range of features that are essential for building efficient and scalable vector search applications. Indexing capabilities allow for quick retrieval of relevant vectors based on similarity, while querying functionalities provide methods to search and retrieve data based on specific criteria. Additionally, TileDB's analytics features enable the exploration and analysis of vector datasets for deeper insights. Component 2. LangChain is a powerful framework for building applications that interact with language models. LangChain is a powerful framework that simplifies the process of building applications that utilize the capabilities of language models (LMs). It offers a collection of tools and modules that streamline the interaction between applications and LMs, enabling developers to focus on building innovative and user-friendly applications. For example, LangChain can be used to build applications that can summarize large amounts of text, translate languages, or generate creative content. Description of the architecture supporting the variable. The architecture involves a robust TileDB vector store designed for efficient storage and retrieval of vector data. The LangChain framework leverages this vector store to enhance its capabilities for natural language understanding and generation tasks. For instance, consider an application that needs to retrieve relevant information from a large corpus of text. LangChain can use TileDB to store and index vector representations of the text, allowing for efficient retrieval of relevant documents based on user queries. This architecture ensures that LangChain can efficiently handle large datasets, enhancing its effectiveness in natural language processing tasks. Explanation of the variable's role in the system. Dependable TileDB import ensures that the vector store is consistently populated with accurate and up-to-date data, guaranteeing the reliability and effectiveness of LangChain applications that rely on this vector store. For example, consider a scenario where a LangChain application is used to provide personalized recommendations based on user preferences. Dependable TileDB import ensures that the vector store used to store user preferences is consistently updated with the latest data, guaranteeing accurate and relevant recommendations. This reliable data flow is crucial for the effectiveness and trustworthiness of the langchain. Application: improved data integrity and consistency. Improved data integrity and consistency are essential for building reliable applications. This ensures that the data used by langchain applications is accurate and up-to-date, leading to more consistent and predictable results. For example, in a customer service application, consistent data ensures that agents receive the most accurate information about customers, resulting in better service and resolution of issues. Reduced data management overhead. Reduced data management overhead simplifies application development and maintenance. TileDB's efficient data management capabilities significantly reduce the overhead associated with data storage and retrieval, allowing developers to focus on core application logic. For example, in a machine learning application, TileDB's efficient data handling can improve training time and reduce the overall development effort. Enhanced reliability and stability. Enhanced reliability and stability are critical for mission-critical applications. This ensures that langchain applications are robust and can handle unforeseen events or changes in data without compromising performance. For example, in a financial application, robust data management ensures that transactions are processed accurately and reliably, minimizing the risk of errors and financial losses. Maintaining data consistency across multiple TileDB deployments. Maintaining data consistency across multiple deployments presents a challenge, especially in distributed environments. Ensuring data consistency across multiple deployments is important for maintaining data integrity and reliability. This can be addressed by implementing robust synchronization mechanisms and data replication strategies to ensure data consistency across all deployments. Ensuring efficient and scalable data ingestion. Efficient and scalable data ingestion is crucial for handling large datasets. Efficient and scalable data ingestion is essential for keeping the vector store up to date and responsive to changing data needs. This can be addressed by implementing optimized data loading mechanisms and utilizing distributed data ingestion techniques to handle large volumes of data efficiently. Langchain community, vector stores, TileDB.get documents array URI. Definition. Detailed definition of the variable get documents array URI. Components. Component 1. A function that retrieves the URI of the TileDB array containing the documents the get documents. Array URI function is a critical component of the TileDB vector store class. It enables the retrieval of the URI that points to the specific TileDB array where the documents are stored. This URI acts as a unique identifier for the array, allowing the system to locate and access the relevant data. Component 2. It is a method within the TileDB vector store class. The getDocumentsArray URI function is a method within the TileDB vector store class, a class designed for storing and retrieving vector data in a TileDB array format. This method forms part of the TileDB vector store class functionality, allowing it to interact with the TileDB array and retrieve necessary information. Architecture. Description of the architecture supporting the variable getDocumentsArray URI. TileDB is a data management system that stores data in an array format. TileDB is a powerful data management system that utilizes an array-based storage structure. This structure allows for efficient storage and retrieval of data, particularly large datasets. TileDB's architecture is optimized for high performance and scalability, making it well suited for handling massive amounts of data. It's an open source system, meaning it's freely available and can be customized or extended by developers. Role. Explanation of the variable S role in the system. It is used to retrieve the TileDB array URI that contains the documents the getDocuments array. URI function plays a crucial role in the TileDB vector store class. Its purpose is to obtain the URI, which essentially serves as the address of the TileDB array containing the documents. This URI is then used by the system to locate and access the data stored within the array. Advantages. Advantage 1. It allows for efficient storage and retrieval of large datasets. TileDB excels in handling large datasets due to its efficient storage and retrieval capabilities. The array format allows for optimized data storage and retrieval, reducing the time and resources needed to access the data. This efficiency is particularly beneficial for applications dealing with substantial data volumes. Advantage 2. It allows for scalable data storage and retrieval. Scalability is another key advantage of TileDB. It can accommodate growing data volumes without sacrificing performance. The system can be scaled horizontally, meaning it can handle increasing amounts of data by adding more storage nodes, ensuring that performance remains consistent even as data volumes expand. Challenges. Challenge 1. The TileDB library needs to be installed. The TileDB library, which is responsible for managing and interacting with TileDB arrays, must be installed on the system. This installation process ensures that the necessary tools and components are available for interacting with the TileDB array. Challenge 2. The function needs to be called with the correct parameters like any function. The getDocuments array URI function requires the correct parameters to function properly. These parameters could include information about the TileDB array, such as its name or location. Providing the correct parameters ensures that the function retrieves the appropriate URI. LangChain community vector stores *rocks has mul sub str. A detailed description of the LangChain community vector stores *rocks has mul sub str feature, outlining its purpose, components, architecture, role, advantages, and challenges. A method to filter a list of *rocks tables by comparing multiple substrings with a specified string. For example, if you have a list of tables named User Data 2023, Product Catalog 2022, and Customer Interactions 2024 and you want to filter for tables containing both user and 2023, this method would return only the User Data 2023 table. Component 1. A table in *rocks database. A columnar database designed for high-performance analytics. These tables typically store large amounts of data and are optimized for querying and analysis. For instance, a table named User Data 2023 might store user information gathered in the year 2023. Component 2. A set of strings to be compared with the table name. These substrings act as search criteria for filtering the tables. For example, the substrings user and 2023 would be used to identify tables containing both these substrings. Component 3. A method to compare substrings with the table name. This operation determines whether the table name contains all the specified substrings. Typically, it involves checking if each substring exists within the table name using string comparison. Functions. Implemented as a function that takes a list of tables and substrings as input and returns a filtered list. This function iterates through each table in the list and compares its name against the provided substrings. If all substrings are found within the table name, it is added to the filtered list. The function then returns the filtered list of tables containing all the specified substrings. filters star rocks tables based on multiple substring matching. This feature allows users to efficiently search for specific tables by specifying multiple search criteria in the form of substrings. For example, if you need to analyze data related to users from 2023, you could use the substrings user and 2023 to quickly identify the relevant tables. Improves search speed by filtering based on multiple substrings. Instead of scanning through all tables, this method focuses on only those that match the specified substrings, significantly reducing search time and improving efficiency, especially when dealing with large datasets. Allows for various filtering criteria by specifying different substrings. Users can create flexible search queries by combining multiple substrings to filter for specific tables. For instance, to find tables containing data about product in 2022, you could use the substrings product and 2022. Matching multiple substrings can impact performance, especially for large datasets. The process of comparing table names against multiple substrings can increase the computational overhead, especially when dealing with a large number of tables. Implementing the logic for substring comparison can be complex. Ensuring that the substring comparison algorithm accurately and efficiently identifies all matching tables requires careful consideration and design. The implementation needs to account for edge cases, such as substring order and partial matches, to avoid false positives or negatives. While TileDB allows for the creation and management of multiple arrays, it doesn't automatically enforce uniqueness for the array names. This means that two different arrays within the same namespace can potentially have the same name, leading to potential ambiguity in referencing the desired array. Description of the challenge to field. TileDB vector index URI can become complex, especially when dealing with nested structures, multiple namespaces, or complex indexing strategies. This complexity can lead to challenges in parsing, understanding, and managing the URIs, especially for developers or users interacting with the system. The langchain community, vector stores, TileDB.get documents array URI. Definition. Detailed definition of the langchain community, vector stores, TileDB.get documents array URI function. Components. Component 1. Tilab is a vector store that enables indexing and querying of vector embeddings and their corresponding documents. This means that you can store and search for data based on its vector representation, which allows you to perform similarity search for documents that are close in meaning. Tilab arrays can be used to store various kinds of data, such as embeddings, documents, images, and audio. For example, a typical application of Tilab is in search engines to retrieve relevant documents based on the user's query. Component 2. Get documents array URI is a function that returns the uniform resource identifier URI of the Tilab array that stores the documents associated with the embeddings. In a practical scenario, this URI might be used in a search engine to retrieve relevant documents based on a user's query. The URI provides the location and access information for the Tilab array, enabling retrieval of stored documents. Architecture. Description of the architecture supporting a langchain community, vector stores, TileDB.get documents array URI function. Tilab stores the embeddings and corresponding documents in a TileDB array. This array can be structured to efficiently store and retrieve a documents and embeddings. In a typical implementation, the array would be organized by dimensions like document ID, embedding values, and document content. The arrangement of data within the array can be optimized for Efficient retrieval in searching based on similarity. Role. Explanation of the langchain community, vector stores, tiledb.getDocumentsArray URI. Functions role in the system. GetDocumentsArray URI is used to retrieve the URI of the tilab array that stores the documents associated with the embeddings. This URI acts as a pointer to the specific location of the documents and embeddings within the tilab system, enabling access and retrieval of the stored data. The getDocumentsArray URI function plays a vital role in connecting the embedding retrieval process with the actual storage location of the documents within the tilab system. Advantages. The function provides a way to access the tilab array that stores the documents. This allows you to retrieve the stored documents associated with the embeddings efficiently. In a real-world scenario, this could be used in a document search application where the user's query is represented as a vector, and the system needs to retrieve the relevant documents from the tilab array based on the query's similarity to the stored embeddings. Tilab arrays can be efficiently queried for documents based on embeddings. This allows you to perform similarity searches using vector representations of the documents, which is a valuable feature for applications like document retrieval, recommendation systems, and image search. For instance, a search engine could use this feature to find documents that are semantically similar to the user's query, even if the query doesn't exactly match any of the stored documents. Challenges. The function assumes that the user has already created a tilab array and has populated it with the documents and embeddings. This means that the user needs to have preprocessed the documents and generated their embeddings before using the function to retrieve the URI. In a practical setting, this preprocessing step involves converting documents into vector representations and storing them in the tilab array. The function returns URI to the tilab array, but it does not provide a way to query the array for documents. This means that the user will need to use a separate application programming interface API or library to query the array based on the embeddings. In practice, this would involve using tilab's query functionality to search for documents based on the similarity between the query embedding and the stored embeddings. Langchain community, vector stores, tiledb.getDocumentsArray URI from group. Definition. Detailed definition of the getDocumentsArray URI from group function. Components. Component 1. This function retrieves the uniform resource identifier URI for the tiledb array holding document embeddings for the specified group and returns it as a string. For example, imagine you have a large dataset of documents organized into different groups based on topics. This function would let you get the URI for the tiledb array that stores the embeddings for documents within a specific topic group. Component 2. This function is used within the tiledb vector store class to fetch document embeddings for a specific group. When you need to retrieve embeddings for documents belonging to a particular group, this function is called to locate the correct tiledb array holding those embeddings. Architecture. Description of the architecture supporting the getDocumentsArray URI from group function. The tiledb vector store class leverages tiledb arrays to store document embeddings and associated metadata. This function enables the store to efficiently retrieve the URI for a specific group's array. This retrieval process allows access to embeddings for documents within that group, contributing to the overall functionality of the vector store. Role. Explanation of the getDocumentsArray URI from group function's role in the system. This function acts as a core component within the tiledb vector store class. It facilitates the retrieval of the URI for a specific group's document embedding array. This URI is critical for efficiently accessing embeddings for documents within that group, enabling various vector store functionalities, such as searching and retrieving similar documents. Advantages: efficiently retrieves uniform resource identifiers URIs for TileDB arrays based on group identifiers, allowing quick and targeted access to document embeddings. For example, imagine you have a system for storing and searching scientific research papers. By using group identifiers to categorize papers by research area, this function allows for efficient retrieval of embeddings for papers within a specific area, enabling faster and more targeted searches. Enhances the overall efficiency of the TileDB vector store class by allowing for efficient lookup of specific group embedding arrays when searching for similar documents within a specific category. This function helps locate the relevant array of embeddings, leading to faster retrieval times and improved search performance. Challenges: improper group identifiers might result in errors or unexpected behavior when attempting to retrieve URIs. If an incorrect group identifier is provided, the function might fail to locate the correct array, leading to unexpected errors or inaccurate results. Efficiently handling a large number of groups and their associated URIs might require optimizations to ensure performance. As the number of groups and associated URIs increases, it becomes crucial to optimize the function's performance to avoid slowdowns or bottlenecks in retrieval operations. Summary of langchain community vector stores utils filter complex metadata. Definition: this function is a core component in the langchain community's vector stores utils library. It acts as a powerful filter for extracting specific information from complex metadata structures. The filter works by taking a dictionary of metadata, a target key, and a corresponding value as input. It then analyzes the metadata and identifies entries that match the provided key-value pair, effectively returning a subset of the original metadata that aligns with the search criteria. For instance, if you had a collection of books stored with metadata including title, author, and publication year, you could use this function to retrieve all books written by a particular author. Components. Component 1. The core of the filter function lies in its ability to effectively match metadata based on specific criteria. This involves iterating through the input metadata dictionary, comparing the target key with the available keys, and checking if the corresponding value matches the provided value. Component 2. Once the matching entries have been identified, the filter function returns a refined subset of the metadata, containing only the entries that satisfy the specified criteria. This refined subset can then be further processed or used in subsequent operations, allowing for focused and efficient retrieval of information. Architecture. The filter function's implementation leverages Python's built-in dictionary functionality and conditional statements to achieve efficient and flexible filtering. The use of dictionaries allows for quick access and comparison of key-value pairs within the metadata, while conditional statements enable precise matching and filtering based on the provided criteria. This combination of data structures and logic ensures a straightforward and effective filtering process. Role. In the broader context of the langchain community's vector stores utils library, this filter function plays a crucial role in providing efficient and targeted access to information stored within complex metadata structures. It enables developers and users to easily retrieve relevant information based on specific criteria, enhancing the overall utility and flexibility of the vector store system. Imagine a scenario where you are working with a large dataset of scientific articles tagged with various keywords and authors. The filter function allows you to quickly isolate articles related to a particular topic or written by a specific author, simplifying data analysis and research. Advantages. One of the primary advantages of this filter function is its efficiency in handling metadata. Filtering. By leveraging Python's built-in dictionary functionality and concise logic, the filter process is optimized for speed and resource efficiency. This is particularly important when working with large datasets, where rapid processing is crucial. Another key advantage of this function is its ability to handle complex metadata structures. The filter can accommodate diverse metadata formats, including nested dictionaries and lists, allowing for flexible and powerful data filtering. For example, if your metadata contains information about individuals, including their names, addresses, and phone numbers, the filter can effectively retrieve information based on any of these attributes, regardless of their nesting levels. Challenges. One of the challenges faced by this filter function is handling cases where the specified key or value might not be present within the metadata. In such situations, the filter needs to gracefully handle these missing entries, preventing errors and ensuring smooth operation. For instance, if you are searching for a specific author in a collection of books, but the author information is missing for certain entries, the filter should handle these cases without throwing exceptions or interrupting the filtering process. Ensuring the accuracy and efficiency of the filtering process is another critical challenge. The filter function needs to guarantee that the returned subset of metadata only includes entries that genuinely match the specified criteria. This involves carefully implementing the matching logic and handling edge cases to minimize false positives and ensure reliable filtering results. Additionally, balancing accuracy with efficiency is crucial, especially when dealing with large datasets. The filter function should strive to deliver accurate results while minimizing the processing time. To optimize overall performance, langchain community vector stores utils filter complex metadata. Definition. A helper function designed to filter metadata within a vector store. It can effectively handle diverse metadata structures such as dictionaries, lists, and nested dictionaries. The function provides a consistent filtering interface for all these structures. Components. Component 1. Filter complex metadata function. This function is responsible for the entire filtering process. It utilizes the filter func for actual comparison. Component 2. Filter func. This function determines the logic for comparison. It takes two arguments, a single metadata entry and a filter value. It returns true if the metadata entry matches the filter. Architecture. The function employs a recursive approach to navigate through nested metadata structures. It applies the specified filter at each level of the structure. Role. This function allows for efficient data filtering based on complex metadata criteria. It simplifies the filtering process by providing a unified approach to handle different metadata structures. Advantages. It offers a unified way to filter data, regardless of the diversity in metadata structures. The filtering process is made easier by abstracting away the complexity of dealing with various metadata formats. Challenges. Handling complex metadata structures can be challenging due to their varied formats. Ensuring efficient recursion and managing edge cases in nested metadata structures is crucial. Langchain Community Vector Stores VDMS client. A detailed description of the VDMS client. Its architecture, role, advantages. and challenges in the context of langchain. Detailed definition of the variable goes here. Components. Component 1. VDMS client is a Python library that provides a simple interface for interacting with the vector database management system VDMS. This library acts as a bridge between langchain and VDMS, allowing users to leverage the power of vector databases within their langchain applications. Component 2. It leverages the power of langchain to seamlessly integrate with VDMS, allowing users to perform various vector database operations. Users can perform tasks like indexing data, searching for similar vectors, and retrieving vector representations of text using the familiar langchain interface. Description of the architecture supporting the variable. Langchain provides a high-level abstraction layer that simplifies interactions with VDMS, enabling efficient and flexible vector database operations. This abstraction layer makes interacting with VDMS easier and more intuitive, allowing developers to focus on building applications rather than dealing with the intricacies of the underlying database. Explanation of the variable's role in the system. VDMS client plays a crucial role in providing a robust and user-friendly way to interact with VDMS from within langchain. It acts as an intermediary, enabling langchain to utilize the functionality and capabilities of VDMS for tasks like semantic search and vector retrieval. Facilitates seamless integration with langchain for vector database operations. This seamless integration enables developers to effortlessly incorporate VDMS into their langchain applications, leveraging its vector database capabilities with minimal effort. Simplifies interactions with VDMS, reducing complexity and development time. By providing a high-level API, VDMS client abstracts away the complexities of interacting with VDMS, allowing developers to focus on building their application logic instead of dealing with low-level database details. For example, instead of writing complex queries to search for similar vectors, developers can simply call a function within VDMS client to achieve the same result. The ongoing development of VDMS client may lead to compatibility issues with older versions of langchain or VDMS as both langchain and VDMS evolve. Maintaining compatibility between these components is a challenge. Users may encounter issues when updating their libraries or need to ensure their application utilizes compatible versions. The library might lack specific functionalities or optimizations for niche use cases, while VDMS client aims to provide a comprehensive interface for VDMS. Certain specialized use cases might require custom functionalities or optimizations. The MMR algorithm operates on a greedy principle, which means that it iteratively selects the best option at each step without considering the global optimal solution. This can lead to scenarios where the selected documents may not represent the most optimal set. Overall, consider a scenario where the MMR algorithm is used to select documents related to quantum computing. Due to its greedy nature, it may not always identify the most relevant and diverse set of documents, potentially missing crucial insights that could be found by considering the entire document set. The algorithm requires a similarity function. The MMR algorithm hinges on the use of a similarity function to measure the relevance and diversity of documents. Defining this function can be challenging, particularly for specialized or complex document types. For instance, when dealing with audio recordings or video clips, defining a similarity function that accurately captures the semantic content and diversity of these data types can be challenging.